So in this section, we're going to start our journey into multi-agent systems. Now, let us begin by developing the right mental model to approach multi-agent systems in LangGraph or multi-agent systems in general. Now, imagine that you have a house and you need to fix a light bulb. You need to fix your light bulb. So the task is to fix a light bulb. Let me get this to medium. So fix a light bulb. Yeah, that's the task. This is a single task, and you probably don't know how to do it. So what do? You call an electrician. So you simply give this task to an electrician. Let's pull that up a little so that, yeah. So you give this task to an electrician. The electrician definitely has knowledge about electrical fittings, fixing electrical stuff, and he comes around with his tools and helps you to fix your light bulb. Simple and straightforward. Now, that's what we've been doing so far. We have been building single agents, specialized agents that perform one task. So you have a task, and you give it to an electrician. And the electrician comes with his tools, with his knowledge, with the instructions you have given the electrician, which is your prompt in this case, and he gets the task done. Light bulb fixed. That's a single agent. One LLM instance with tools, or can be multiple LLM calls with tools, a system prompt, and a conversation history. And everything happens in one context window, one decision-making loop. That is what a single agent does. A single specialized agent, just like the one we have seen with the create agent, react agent. You build an agent that is specialized to perform one task. Now, what if you want to renovate an entire apartment? You want to renovate your entire apartment. That is not one simple, straightforward task. So now the task is to renovate apartment. So you need to renovate your apartment, and part of the tasks involve electrical work. There's going to be some plumbing work. There is going to be probably some wood work. You might want to have POP fittings. You might want to have a garden outside and all sort of stuff. So despite this being a single goal, which is renovate apartment, it consists of several tasks. And most likely one person is not going to handle all that task, except you have a G.I. Joe handyman that just knows how to do everything. But no, most of the time you will need to delegate to different experts. So for electrical stuff, you call your electrician. For plumbing tasks, you call a plumber. For gardening tasks, you call a gardener. And I'm sure you get the gist. You call a gardener. So you call these guys and you delegate tasks to each of them. Each of them have their own set of instructions. Each of them come with their own set of tools, and each of them have their own area of expertise. This is how a multi-agent system works. When you have a goal that involves several specialized tasks, you need to build a multi-agent system. And with a multi-agent system, you get to break down this goal, have multiple agents, each with their own specialized prompts, their own focus tools, isolated context, and all connected through a coordination mechanism. Meaning that you have to coordinate the activities between all these guys, because some of their tasks can be done in parallel, whereas some of them have to complete their task before another expert can take over. Did I spell gardener well here? No, I don't think so. Let's fix that. Gardener. Yeah. Not gardener. So, sometimes their tasks can be done in parallel. So let's say the electrician and the gardener can be working simultaneously. I don't think it's going to be on rare occasions where the gardener has to wait for the electrician to finish his work, or the electrician has to wait for the gardener to finish his work. But the electrician and the plumber might not be able to work at the same time. You might want to finish your electrical work before you start plumbing, or you might want to finish your plumbing work before you start the electrical work. All these coordination systems, we're going to be seeing them in the way of design patterns going forward. We're going to be looking at different design patterns that can be used to implement multi-agent systems, and we're also going to be looking at how state is managed. So, multi-agent systems are all about dividing cognitive labor. Dividing cognitive labor. Just as organizations divide work among specialists, multi-agent systems help you divide AI work among focused agents that excel in their own domain. So yeah, that's simply multi-agent systems. Next, let us look at the anatomy of a multi-agent system. Before we do that, I'm just going to put this in a frame. I'm going to put everything here in a frame. Yeah, I like properly organizing my stuff, so let's just have all this in a frame. Now, the next thing we're going to look at is the anatomy of a multi-agent system. Anatomy of a multi-agent system. Let me just bump that up a little bit. So, anatomy of a multi-agent system. What are the things, what are the components that a multi-agent system comprises of? Now, the first is agents, for sure. Agents. So, we have agents. And as I have described, these are independent units with their own LLM, prompt, tools, and state access. We're already familiar with agents already, so there's no need to go deep into that. Independent units with their own LLM, prompt, tools, and state access. Now, the key decisions that need to be made when you're building your agent is, first, you have to determine how specialized they have to be, what tools per agent, and what's going to be the personality of your agent, and of course, what are going to be the constraints of your agent. So basically your agent's scope. So how specialized, what tools your agent has access to, and also your agent's personality and constraints. The second thing that comprises of a multi-agent system is the coordination mechanism. Coordination mechanism. Now, this defines how your agents work together. From the definition, a multi-agent system consists of different agents working together. So you have to define how they work together. Who decides the routing? How do the agents communicate? What even triggers the transition from one agent to another? And as I mentioned earlier, we're going to be seeing that in our multi-agent design patterns. We're going to be looking at different multi-agent design patterns in this section. So that is all going to become very clear very soon. The next component is state management. State management, very, very important. How do you manage data flow across agents? What information stays persistent across agent interactions? What is shared? What is isolated? And how does context flow through and between your agents? So that's basically what we're going to be looking at in state management. And when we start looking at design patterns, you will see how each design pattern helps you manage state. Lastly, we have entry and exit points. Entry and exit points. Now, basically, what this defines is the interface with the users, the people that are interacting with your multi-agent system. At which point do they enter data? Which agent is talking to them? Can all the agents talk to them? And also, how do the agent or agents get to respond? Yeah. Entry point, which agent is talking to them? How many agents can talk to them? Exit point, which agent replies them? How many agents can reply them? So, that's basically the four components of a multi-agent system. Agents, which are the specialized components doing the work. What is your coordination mechanism? Who is making the decisions? How are the decisions made? State management, how does data flow through and between agents? Which data is isolated? Which data is shared? And also entry and exit point, which agent or agents get to talk with your user, and which agent or agents get to respond to the user of the multi-agent system. So basically, that is the anatomy of a multi-agent system. Now, the next thing we're going to be looking at, and I'm just going to create a new frame for that, we're going to be looking at when multi-agent systems make sense. When do you actually have a multi-agent problem? because you don't want to use a multi-agent system when you don't need one. So when does it make sense for you to use a multi-agent system? Let's have that title up there. That will be when multi-agents make sense. Because half of the process of you building an agentic system is making the right decisions. You don't want to over-engineer or have overkills. So when does it make sense to use a multi-agent system? Let me make that extra. Okay, yeah. When multi-agents make sense. First is when you start noticing that you have a tool overload problem. A tool overload problem. Yeah. When you start building a single agent and you start making it godlike, can do everything, and you notice you are having up to 30 tools or more, that is going to confuse your LLM and it will start making poor tool choices. And a lot of times it's going to even start confusing tools or picking irrelevant tools. So once you start having up to 30 tools and more, then you should break things down. You know that you have gotten to an inflection point and you have to actually break things down. Distribute tools across specialists and have if you have 30 tools, break them down into 3 specialists and give each of them 10 tools. So when you start noticing a tool overload, that is a trigger that you might have to redesign your system from a single agent approach, from using a single agent approach to a multi-agent strategy. So that's the first thing when you have tool overload. The second trigger to you knowing that, yeah, it's time to introduce a multi-agent strategy is when you start facing context window limits. When you start facing context window limits. Traditionally, single agents use one LLM, so one context window, and quality begins to degrade as conversation grows. Once you start having long conversations with your agent, imagine a user keeping an agentic session on for days, and not just days of being dormant, no, active days. The quality of the conversation would definitely degrade. The agent will start to forget things, to start to miss context. A lot of times, I talk to Gemini and it just gives me the wrong thing. Like, it just starts talking about something I didn't refer to. Like, there was a time I was using Gemini to generate descriptions for my YouTube videos, and I'll give it a topic and it will just go and pick an old description. then I'm going to correct it and I'll be like, oh yeah, sorry, I forgot, yeah, blah blah blah. And also Claude, let me move on the screen so that you know that your screen is not frozen. Claude did something interesting recently. I was trying to resume a conversation and it told me that it is going to compact all our previous conversations because I hadn't talked to it for like 2 days. So it just popped up in a progress bar and the message was compacting previous conversations. And I know what it was doing behind the scenes was that it was summarizing the memory system, because there's this map reduce strategy you can do with your long-term memory and short-term memory, and you can use it to kind of summarize the previous conversations so that it still makes sense for preceding interactions. So context window management is something that you have to deal with a lot. Some models have large context windows. Gemini started giving us 1 million tokens in the context window, even though there are models in Gemini that give 2 million. But Anthropic, I don't think Anthropic has even cracked the 500k limit. Anthropic is always very, very conservative. So I don't even think they've cracked the 500k context window limit. So when you see that, when you notice that for each, as the conversation with a single agent grows, which is, if you see that as a possibility, there's an indication that the context window can grow beyond necessary and you want to split things up. So you do context isolation where each agent works with only what it needs. You break things down and you are able to give different agents different small pieces of the information, subsets of the information, so that they can work on it separately and each one does not exhaust the available LLM context window. So when you start having context window limits, That's another indication that you have to use a multi-agent strategy. Another indication is when you start having sequential constraints. Sequential constraints. From the graphs we've been building, and even from the single agent that we've built using the create agent pattern, which definitely uses the React pattern under the hood, everything just flows. So if we have a workflow and it has point A, point B, point C, point D, everything just flows. But what if you have constraints? What if you have to process A and be done with it, or have a verification check before you can then move to point B? Yeah. What if, for example, in an account system, you have to verify your identity before you get account access, and also maybe you apply for a refund, but they need to verify your warranty before you can get the refund? If you have those constraints, then you might want to introduce a multi-agent strategy, because with multi-agent you can architecturally enforce a handoff from one agent to another agent, or from one step to another step. Agent B will be literally unreachable until agent A completes. Agent B will be unreachable until agent A is done with his task. We're going to be looking at a design pattern later called HandOff that is very perfect for this type of scenario. So when you want to introduce sequential constraints, you might also want to consider a multi-agent system. Another indication is when you have strong parallelization needs. When you have strong parallelization needs, if tasks need to run, or rather, if tasks can run in parallel, you should not make them run sequentially. They should not run sequentially. Like using the renovation analogy that we discussed earlier, your gardener shouldn't have to wait for your electrician. Your gardener shouldn't have to wait for your electrician. Your electrician also shouldn't have to wait for your gardener. Why do you want green grass before you can light up your house? So it's unacceptable latency, because independent subtasks can run sequentially. So you can use a multi-agent system to dispatch tasks to specialists simultaneously. You dispatch tasks to specialist agents simultaneously. So that's one more indication. The last one we're going to discuss is when you have organizational boundaries. Organizational boundaries. When you have organizational boundaries, then that's an indication that you should use a multi-agent system. Now, as a rule of thumb, if you are going to be designing any kind of thing that has an organizational structure, you have to go with multi-agent systems. Yeah, you have to go with multi-agent systems. You can't be designing agency and it has sales on one side, it has support on one side, it has engineering on one side, and you're trying to cram everything into a single agent. Now, that's not going to work. So once you look at your task and it looks like an organizational structure, just go with multi-agent system. Just go with multi-agent systems. And also, when you need different teams to support different aspects of your agentic system, for example, you have an agentic system that has a sales department, it has a support department, it has an engineering department. Definitely, you want to devote each agent to different teams in your development team. In your development team, you want to give each agent to different teams. This is kind of like the same heuristics that is used to determine whether you should use something like a microservices system. A microservices architecture is not just something you just pull out as a silver bullet to solve all your problems. Once you notice that the way your application is being built, you need to devote different parts of your applications to different teams, you might want to consider using a microservices architecture. So it's something that it is indicated organizationally, not even by complexity. So each team owns their agent, and you develop a central layer that composes everything. So these are your triggers to know when a multi-agent system is required to do the work. But if everything is still simple and focused, you have like less than 15 tools, if you have tight latency requirements, because multi-agent systems do add their own latency overhead, but if you have tight latency requirements, if you have limited budgets, That's another thing. You have to consider how much resources you have to develop also. And also when you are in early development stage, just go with single agents. But if you tick 3, sometimes even 2 of these boxes, you want to consider using a multi-agent approach. Anyway, now let us talk about benefits. Let's talk about benefits. Yeah, I think we can fit benefits in here. Let me see if I can highlight all this. Yeah, good. So we can fit benefits somewhere here. So what are the benefits of using a multi-agent system? The first we're going to be discussing is better accuracy. Better accuracy. Let me take this down a notch, okay? So the first is better accuracy. Specialists always outperform generalists in their domain. Yeah, specialists will always outperform generalists. I think there's this saying I heard that there is nothing that does 2 things that is the best at one of them. There's no component that does 2-3 things that is the best at one of them. So just an anecdotal saying to make you understand that, yeah, you most likely won't be able to outperform someone that is a specialist in their own domain. Yeah, you can't outperform such kind of people. A gynae might know all about childbirth, but if you're going to be going under the knife, you would need a surgeon to come and perform a CS operation. Yeah, so just speaking from some experience there. So yeah, you specialists will always outperform generalists in their own domain. So that's the first thing. The second thing is better tool selection. Better tool selection. When you have an agent that is given fewer tools to work with and has a better understanding of his domain, it will make better choices. That agent is going to make better choices. If you give a generalist agent 50 tools, just be prepared for your agent to go off the rails. But if you give a specialized agent 5 tools, 7 tools, or at most 10 tools, then you get better performance. Then you get better performance. Then you can rest easy knowing that your agent would make better decisions. So that's another thing. Also, there is the case for maintainability. Maintainability. A multi-agent system is going to be easier to maintain because you can test your agents independently. You can test their capabilities independently. You can write evals for them independently. You're not trying to write evals for an entire multi-agent, an entire monolithic agent that does like 50 different things. No, you test. You can test your agents independently. You can reason more about your system compositionally. So that's and like we said, even your team is easier for your team to manage different agents, and you don't have this single point of failure. If one agent goes down, the entire system doesn't have to go down. Which would be the case if you have a single agent that is trying to do a lot of things at once. So yeah, that's another benefit for using multi-agent systems. Another one is parallel execution. Parallel execution. We've discussed that already, so I don't need to say much on that. But like I said, if tasks can be performed simultaneously, don't run them sequentially. That is just taking a latency cost that is very, very avoidable. So you can process with multi-agents, you can process independent subtasks simultaneously. Another thing is what we refer to as graceful expansion. Graceful expansion. Graceful expansion. Now, what this means is that when you have a multi-agent system, you can easily add more specialist agents without destabilizing the entire system. Yeah, you can add more sub-agents. For example, in our renovation analogy, you've called an electrician because you need electrical work done. You've called a plumber because you need plumbing work done. Your gardener is doing a thing. And you want to fix internet. Yeah, you want internet connectivity in your house. You don't have to you don't have to disrupt others. You just add a provider and they will come with their tools and get it all set up. Find some of their tasks can be dependent on the electrical guy, but still you can just add them without disrupting any other person's work. If you had a single, like I said, GI Joe handyman handling everything, and he's currently doing electric work, then you tell him, oh, I need internet connection. He will tell you, you have to wait. You would have to wait. Let me be done with this, then I can move to that. But for a case where you have proper division of labor, you just call the other guys, and you can even use a different provider. You don't have to have the same person giving you electricity, giving you internet connectivity. You can use different providers. So graceful expansion, you can easily expand, you can easily make your system better, and you can also easily remove. You can remove. If you don't need an electrician anymore, you just remove the electrician. That's done. Other people continue with their work. So that's another big advantage to using multi-agent systems. And lastly, we'll look at something called enforced compliance. Enforced compliance. Because you have multi-agents, you can easily build guardrails between how they interact, how they share information, and even how information is isolated. What information goes to where. So your business rules have become structural, not advisory. You don't have to go to your prompt and be prompting your agent to hell on what it should do or what it should not do. You can simply implement that within the structure of the system, so that it's either a possibility constrained with guardrails, or it's not just going to happen at all if you don't want it to happen at all. Agent A never sees agent B's information. Whereas in a monolithic system, when you have a single agent trying to do everything, each task is exposed to all the data for tasks that don't even concern it. So enforced compliance. Those are your benefits. So now that we've looked at benefits, let's also look at trade-offs. Take benefits here, and let us look at trade-offs. There is no perfect system. Every system comes with its own trade-offs. That is the whole world of architecture. So what are the trade-offs to using a multi-agent system? What do you have to be aware of? What are the caveats? The first thing is increased latency. Increased latency. Okay, let me get that down a notch. So increased latency. Every agent transition is one more LLM call. So all that moving around, all that information bus, that's just extra latency. Just like a microservices architecture. Or rather, just like in a microservice architecture. So increased latency, increased communication management and stuff like that. So you have to be aware of that. A single agent system is definitely going to be faster than a multi-agent system. Second, we have higher costs. Higher costs, which also kind of ties into the whole latency thing. So you get a lot of repeated calls. For example, in a sub-agent pattern that we're going to be looking at later, the sub-agent communicates to the agent, then the agent has to communicate back. The sub-agent communicates to another agent, the agent has to communicate back. So all that back and forth is going to cost you more tokens. So that's another thing to be aware of. Also, there's more complexity. Like I said, there has to be an information bus system where you decide how information is going to flow, how it's going to be managed. Also, you're dealing with different agents, so there's a lot of contracts amongst them that need to be fulfilled. Debugging becomes harder, and more failure modes, and even you have to manage a lot of consistency issues. So you are definitely dealing with more complexity here. Nothing comes for free, isn't it? So more complexity. Now, also conversation coherence. Conversation coherence. Now here, you have to manage the information in such a way that when each agent gets their task, they need to have everything they need for their task. In a pattern that we'll be looking at later called handoff, when one agent completes his work and hands off to another agent, the handoff has to be pristine in such a way that the new agent has everything it needs. It doesn't like miss any context. So everything has to be consistent. If you have a case whereby the whole flow starts feeling inconsistent to some agents. They will not know what to do. They will just hallucinate or just go off the tracks. So yeah, these are another complexity that you have to manage. You have to make sure that the conversation between your agents is coherent. Each agent understands what's going on. Each agent knows what to do, and each agent has everything it needs to do what it needs to do. So yeah, those are your trade-offs. But in a situation that requires a multi-agent system, this is totally worth it. This is totally worth it, because a bunch of situations are out there that you can only attack with a multi-agent system. So you should be ready to deal with all this. It's all part of engineering. So now that we've looked at when agents make sense and the benefits and trade-offs, let us take a look at what all this looks like in line graph, just from a very zoomed out level. What all this means in line graph. Framing, let me get this out. So what do we title this? Let's just say the graph abstraction. So the graph abstraction. Definitely could have given it a simpler name, but yeah, let's just roll with that. So the graph abstraction, what does it mean? How do these things, or how are these things represented in what we've learned so far in line graph? So first, nodes. Your nodes, what do your nodes represent? In a multi-agent system, your nodes represent your agents. They can represent your agents. They can also represent your functions, tasks, stuff you need to do, and they can just represent a particular computation. For example, in a pattern known as the routing pattern, there's a step where it just categorizes a task. So that's basically just a computation. Or you can also take it as a function. So yeah, that's what your nodes represent. Agents, they can be the agents themselves or the sub-agents. They can be functions, and they can just be computations. So that's nodes. So what about edges? What do edges represent? What do edges represent? Edges are simple. They are simply your transportation mechanism. So, transition between agents, basically. So they do what they know how to do best. They help you move between agents. They are what you're going to use to determine the routing pattern that goes on within your multi-agent system. Next is state. What does your state represent? The state. And state represents the information flow. Information flow between agents. Yeah. Your state represents your information flow between agents. Your edges represent your transition between agents, both your direct edges and your conditional edges. You can use your conditional edges to do runtime routing decisions. And your nodes represents your agents or your sub-agents, your functions, your computations, and all that. So yeah, that's what these core elements represent. Did I get everything? Okay, yeah, good. That's what these guys represent. Now, what about some other stuff that we know? Some other stuff we've worked with. Things like checkpointing and stuff. For checkpointing, that's persistent with short-term memory. So checkpointing, if you want your multi-agent system to have memory between runs, which you most likely want, but sometimes it's just a single turn. A single turn can solve your task. Probably it's just a one-shot thing. It's just a one request thing, and it just runs through one turn and it's done. But if you're going to be coming back and you're going to be asking follow-up questions, you're going to be giving follow-up tasks, follow-up instructions, you want to make sure that your multi-agent system has a checkpointer. And the good thing about checkpointing in line graph is that it flows down. So once you give the main agent, if you give the overall system a checkpointer, it flows down to all the sub-agents. So checkpointing helps you to persist for long running and resumable workflows. Then we have command and send. Or let's just say command first. Command does what it does. You use it to update state within a sub-agent. You can update state within a sub-agent, and you can also use it to navigate to another agent, another downstream agent. So basically what we know about command, but in multi-agent systems it becomes even more handy, as you can use it to dynamically update state and also dynamically navigate. And we have send. Send is going to be our main tool for parallel operations. So anytime you need to dispatch operations in parallel, anytime you need to dispatch tasks in parallel, you definitely want to use send. You want to use send. So that is what multi-agent systems look like in LangGraph. Now we're going to wrap up this video by looking at the different design patterns. This is not where we go deep into the design patterns. We're just going to discuss them because we can then look at each one later in full detail in other videos. But let us look at design patterns available in LangGraph for building multi-agent systems. So design patterns. Just going to briefly discuss them and get you excited about them. So the first pattern is sub-agents. Sub-agents. In a sub-agent system, you have a main agent that serves as a supervisor and coordinates other specialists, which are sub-agents, to do their tasks. So that's basically what sub-agent does. It's very, very aligned with the whole innovation strategy. You are the main agent, you are the coordinator, and you're coordinating different specialists to do their job in your house. So sub-agents, that's your first pattern. Next, we have another pattern known as handoffs. Handoffs. The handoffs pattern. Now, what happens in the handoffs pattern is that when you have a goal and you know that goal can only be achieved by having different specialists, but you have a very sequential flow. One guy finishes his work, then he hands off to another one. That one finishes his own work, then he hands off to another one. That is where you use the handoffs pattern. There's no coordinator basically. One guy starts, hands off to the next one, and the next one picks up the task from there, continues, stops at the point, hands over to the next one. So peer-to-peer transitions. That's what goes on in the handoffs pattern. The next pattern is the skills pattern. And I'm sure you've heard skills a lot these days. There's a whole skills hype train in Cloud Code and some other AI tools all over X, Twitter, all over LinkedIn these days. So yeah, it's the skills pattern. Now the skills pattern is basically like a shape-shifting agent. It's actually one agent, but that agent has the ability to load different skills based on what you want. So it's like that G.I. Joe handyman actually. An handyman that has a lot of knowledge. He has electrical knowledge, he has plumbing knowledge, he has gardening knowledge, he has upholstery knowledge, he has even knowledge of POP. So when you want to do POP, it just loads POP knowledge. When you want to do electric work, it loads the electric knowledge. So that is what the skills pattern does, self-augmentation on an as-needed basis. And the last one is the router pattern. The router pattern, which is specifically designed for you to dispatch tasks in parallel. Once the task needs to be dispatched in parallel, different operations running at the same time, not conditionally, but by design, you use the router pattern. So what the router does is that it takes a goal, breaks it down, dispatches it in parallel, and synthesizes the results. That's basically what it does. Then you can always build a custom flow. We've learned LangGraph enough that you can build any type of graph. You can direct your graph in any way. So if your task doesn't fit into any of these patterns that we're going to be looking at in more detail later, if your task doesn't fit into any pattern, you can just go raw and design your graph from scratch in whatever way, use an hybrid of different patterns, use your own custom flows, custom design, whatever you design flows here. So yeah, design patterns, that's the last thing we're going to be discussing here. Just as a quick bonus, I'm going to show you like a preview. I did a diagram of all these patterns, but we're still going to be looking at them later. But yeah, this is a preview of the different patterns. This is the sub-agent pattern, a coordinator giving tasks to different specialized agents and getting feedback. Handoffs, one agent handing off to another one. Skills, loading skills on demand from a whole toolbox. And the router pattern, which definitely splits tasks in parallel and synthesizes the results from the specialized agents that have worked on it. So yeah, this is multi-agents. This is your introduction to multi-agents, and from here you can pick this knowledge and start extending it through the lessons that are going to be coming up next. In this video, we're going to be discussing and really looking at the sub-agent multi-agent pattern. This is going to be the first multi-agent system pattern that we're going to be looking at, the sub-agents pattern. Now imagine you're the HR at a company. So this is you, HR. And the boss says, let's get a text. The boss says, it's Susie's birthday. Make sure you organize something special for her. So, as the HR, you get into action. What would we need for Susie's birthday? Definitely won't want to miss out on a cake. So you need to call a baker. You need to call a baker to get a cake. Now what next? We need balloons. We need to have the staff room decorated. So yeah, definitely we need a decorator or an event planner or whatever. Let's just say decorator. Let's call them that. Decorator to make sure that the staff room is decorated and everything is nice for Susie's birthday. Then we'd like to eat something. So let's get a caterer. Let's use blue for that. So let's get a caterer to take care of that. So you're calling these guys, and as you prepare, you communicate with the baker, get the status of the cake. You guys communicate back and forth. The baker gets back to you, gives you the progress report, and definitely tells you when it's done. So you get that information. Then you also communicate with the decorator, who also gives you their bill. You negotiate to get everything done. They implement. They get back to you. All this communication going on. Sometimes simultaneous, sometimes not simultaneous, but communication is going on between you and these guys. And at the end of the day, you make sure that everything, all their tasks, is harmonized, and Susie gets a birthday. So the CEO gave you a task to plan Susie's birthday, and you have just executed it. Say plan Susie's birthday, and you have just executed it by calling on different specialists to handle the tasks. You are managing the communication back and forth with all of them, and you are making sure that everything is harmonized. The decorator doesn't go and decorate the yard instead of the staff room. The caterer gets the food there on time, and you make sure that you give the caterer necessary information, how many people are going to be eating, some extra plates in case some people bring guests along. You make sure that the baker bakes the correct type of cake you want, doesn't misspell Susie's name, delivers it on time. So you manage all that, you coordinate all that, and at the end of the day, you can get back to the CEO. These guys don't talk to the CEO. You get back to the CEO on the status of Susie's plan. When the CEO asks you, what's the status on Susie's birthday plan? How is it going? You get to respond, fine. Oh, the baker will deliver at so time. Oh, we'll have the room decorated, or the room is already decorated. The food has been delivered, and all those kind of stuff. You get to communicate with the CEO. These guys don't communicate with the CEO. These guys communicate with you, and you synchronize all the operations and get back to the CEO. This is exactly how the sub-agent pattern works. This is exactly how the sub-agent design pattern works. It's a multi-agent system where you have a central main agent who coordinates specialized sub-agents, synchronizes their work, and makes sure that the appropriate response gets back to the user. So here we have HR. You as the HR. In a sub-agent system, you are the coordinator. You are the coordinator. The baker is a sub-agent, because sub-agent 1. The decorator is another sub-agent, because sub-agent 2. And the caterer is another sub-agent. I'll call the caterer sub-agent 3. Yeah, that is how the sub-agent pattern works. That's basically how the sub-agent pattern works. Now, let us look at the characteristics of this pattern. The attributes you're going to see in a multi-agent architecture, and you'll be like, yeah, this is using sub-agents. This is using the sub-agent pattern. And the first is centralized control. Centralized control. That's the first thing. Let me write characteristics here. Characteristics. Yeah, be cool and do X. So characteristics of the sub-agent pattern. The first is centralized control. There is a main agent who is the coordinator. There's a main agent that makes all the routing and delegation decisions. All the routing and delegation decisions is made by this main coordinator agent. Not this guy, not this guy, not this guy. This guy makes all the decisions. So that's the first thing. One main agent is the one leading the orchestra. That's the first thing. The second thing, and this is from an implementation standpoint, is that your sub-agents are tools. Your sub-agents, while being agents, let me spell this correctly. Your sub-agents, while being agents, are implemented as tools. They're implemented as tools. So what you do is that you create these sub-agents with create agent or with a land graph. You create them and you expose them as a tool to the main agent. You wrap them as a tool. You use a tool definition, you create a function, you call the agent within the tool, you return its response, and then you can give that tool to the coordinating agent, the main agent. Yeah, that is a very key part of using the sub-agents pattern. Your sub-agents are exposed to the main agents as a tool, as tools rather. They are exposed to the main agent as tools. Now, the third characteristic, which I have discussed, but we're going to emphasize again, is that there's no direct user interaction between your sub-agents and your user. Yeah. Between your sub-agents and the user, giving you the task, giving you the query, there is no communication between them. There's none. There's none. They can't go behind you to communicate with the user. So this central agent is the one leading the pack. These guys don't get to communicate with the user directly. They don't get to communicate with the user directly. Just as these guys that you have contracted for Susie's birthday don't communicate with the CEO. They don't communicate with the CEO except you don't get them paid and they decide to go rogue on you. Yeah, which is definitely within their rights. But yeah, they don't have any reason to communicate with the CEO. They don't have any reason to communicate with the CEO. You manage everything, payments and all that. Another thing, another characteristic of this design pattern is that there is context isolation. Context isolation. Now, what this means is that each sub-agent works in a fresh context. Each sub-agent works in a fresh context. No memory of past calls. You call them once, they do their work, they return it. You don't inquire of their work like, yeah, those stuff I give to you, what about they're not going to That you get to keep all the context. Yeah, you get to keep all the information. You get to keep all the state. So let's say you tell this guy that you want red velvet cake. It makes red velvet cake. If the CEO asks you, which type of cake did we make? Don't go and ask this guy. He doesn't remember anymore. He doesn't remember. You have to remember that it's red velvet and respond to the CEO. And the CEO says, yeah, I would prefer a chocolate cake instead. Then you have to go back and give this guy new instructions for a chocolate cake. Give it new instructions for a chocolate cake. It can't reference any previous information about this. By the way, why am I pointing to the caterer for cake? Sorry. cake instructions go to the baker. Cake instructions go to the baker. Sorry about that. So yeah, there's context isolations, and these agents are stateless. They are stateless. They don't remember past invocations. No, they don't remember previous invocations. So that's another thing you need to keep in mind. And also, they are isolated from each other. This guy doesn't know what this guy is doing. Yeah, the baker doesn't know what the decorator is doing. The caterer doesn't know what the decorator is doing. So you are the one to hold all that information and make sure that you give the decorator the right information so that it doesn't mess up whatever the caterer brings. For example, the staff room is decorated, but there's nowhere to put the cake. Yeah, you are the one that is responsible for that. You are the one that didn't give the correct instructions for the caterer to be able to, or rather for the decorator to be able to make sure that, yeah, there should be a stand for the cake. So that the last one is result synthesis. Result synthesis, which we have also kind of discussed, meaning that you are to collate everything that comes from these guys. Everything that comes from these guys, you are responsible for collating everything, making it make sense, and reporting it back to the user. The coordinator is responsible, the main agent is responsible for combining all the outputs from the sub-agent into a coherent response for the user. So yeah, that is the final characteristics that we're going to be looking at. Now let us look at the process flow, and we don't need to leave this diagram to better understand the process flow, but we're going to look at it in stages. Each stage of how the entire process flows through this multi-agent pattern, the sub-agents pattern. First, the request is received. So a user sends query to the system, to the entire multi-agent system, sends a query, and that query is received by the main agent. The main agent receives this query. Now, the main agent will then make a routing decision. It has to make a routing decision. So what it first does is that it analyzes the request. And decides which sub-agents to call. And this is very important, because it doesn't have to call everybody. The fact that it has a baker, a decorator, a caterer, what if it was just a simple birthday that needs to happen in like 15 minutes? So we're not going to have time to sit down and eat. So with that, even though it has the contact of a caterer, it doesn't need to call. The caterer, just calls the baker and a decorator. Sometimes you can even keep it so simple, you will just only call a baker. We just want to snap a few pictures with our name on the cake, blow some candles, and be done. Then it will just simply call the baker. So the context of the task also determines who is called. Not everybody has to be called. So it makes that routing decision and decides who to call. And remember, they are wrapped as tools, so this main agent calls them as tools, but they are actually sub-agents. So what happens? It calls the sub-agent it needs to call. They execute their tasks, and they all return their responses. It's a one and done thing for them. They get the call, they operate, and they return, and their entire context is cleared. They don't have any memory of what just happened. So that happens. All the results flow back to the main coordinator based on how many sub-agents actually worked on it. Then the main agent will then synthesize. So it would combine all the results and then provide a final response. And hold all the context. If it's using a checkpointer, it will hold that memory, and you can requery it. But these guys don't get to hold the memory. He manages all the information and all the flow. So that's how that happens. Now, before we proceed to our next talking point, I want to go back to this context isolation and why it matters in subagents pattern, because you might want to ask yourself, why is it that these guys can't keep context? Wouldn't it be nice for them to keep context? So let's discuss that. First, the fact that you have context isolation prevents context bloat in subagents. We're trying to manage context windows, so we want to trust the coordinating agent to give them what they want, to give them all the context they want as needed. So we don't want to store context here and bloat up the whole context window for this subagent. It will be very, very redundant and wasteful. So we want this guy is going to be responsible for all that intelligence to give these guys exactly what they need. Even if they need to refer to something that happened previously, it should bundle it up in the context so that they can refer to that to provide grounded responses. So yeah, that's the first thing. Number two, it keeps them focused. It keeps them focused on only the context they need. If you are storing extra context here, they would always refer to it. And some of those context information is already stale. They don't need it. So it's better to clear them each time so that they only get what they need. And this guy is going to be doing a lot of heavy lifting. Yeah, this guy is going to be doing a lot of heavy lifting. So this guy is going to be the one to make sure that they get only what they need. Subagents can be confused by bloated context. They can be confused by irrelevant history. So you don't want to pack anything inside that will make sure that they don't do their work in a focused manner. And we're going to delegate all that heavy lifting to the coordinating agent. So basically, that is why we want to keep our sub-agents stateless in this particular design pattern. Now, let us talk about some design decisions. I think I can still have that here. Design decisions. Some design decisions when working with let me put asterisks here to show that these are the headers. So just something there. Yeah, something like that. So characteristics, here we have design decisions. Yeah, okay. That should work. Okay. So what are some design decisions that we need to make when we are using the subagents pattern? The first thing we need to ask ourselves is that, do we want the execution of each subagent to be synchronous or asynchronous? So sync versus async. Sync versus async. Do we want it to be synchronous or asynchronous? If it's synchronous, then the main agent would have to wait for a subagent to complete before it calls another subagent. It will have to wait for it to complete before it calls another subagent. Now, this is useful when you need the results of a particular subagent before you call the other one. Maybe the baker, probably the decorator is looking for the right table or the right team for the table that will carry the cake, something like that. I'm not an expert. And the baker needs to be done so that you will know, yeah, this is the size of the cake and this is what to weigh and everything, so that the information can be passed to the decorator and decorator knows the appropriate type of cake stand to bring. So yeah, that can be useful. Sometimes these tasks are dependent, have to happen in a particular order. Then you would need to run stuff asynchronously. So that can happen. That can happen. So you have to make that decision to either run this guy synchronously or asynchronously. But because you define them as tools, a lot of times your coordinator is going to be making that decision for you. Anything that can be run simultaneously, to run them simultaneously. Anything that has to wait would wait and would run immediately after the dependents are done. You should also try and provide something like that in the set of instructions that you are giving to your coordinator. So in a situation where you want to run things asynchronously, that you run things asynchronously, the main agent is just going to continue while the subagents do their work in the background. Just going to continue. For example, the baker and the caterer can just keep working. Yeah, the baker and the caterer can keep working, and they don't have to block each other. The baker and the caterer don't have to block each other. This is very, very important for long running tasks. If you have any long running independent tasks, you want to make sure that you're running them asynchronously. For example, you are doing some research, you are compiling a report and stuff like that. You're researching different sources to get information. You should run that asynchronously. So that's one thing. The second is what each sub-agent receives. What if sub-agent receives? Now, a lot of this, I want to point out at this point, no pun intended. I want to point out at this point that a lot of these decisions are more important when you are doing things from scratch, or you're doing a custom flow, doing things from scratch, doing them with graphs and all that. If you use the create agent, react agent, it would make a lot of these decisions for you. But if you are doing things from scratch, which you might have to do a couple of times, you need to these decisions are very, very important. So you want to decide which information goes to each sub agent. You can decide to pass them the query, only the query. You can just take the whole context and just pass them the query. Yeah, this is what the user wants, this is what you have to do. So it just gets a specific task question. Like for the baker, you just simply tell the baker, bake me a 3-layer red velvet cake with buttercream frosting. So you just give them the specific instructions they need. So sometimes you just pass only the query. Other times you want to pass the query and some context. Like I said, they are stateless, so any context they need has to come from you. So sometimes you just pass them the task they need to handle, or you can pass them that task with some context. Pass them that task with some context. That's another thing. So they can have the sub agent can get a subset of the whole conversation history, or you can just give them the full access. Same full access you have, you give it to them. That would probably not be needed most of the time to pass the entire set of state keys to them, and also it can lead to tight integration. Sometimes that is needed. Sometimes you need to tightly couple them, but most of the time you wouldn't. So, but yeah, you have the ability to do that. You have the ability to pass the full state to your sub agent. So that's the other decision you need to make. Should you pass the query, just the query? Should you pass the query and the context and some context, or should you just give them the entire state? You just give them the entire state with all the state keys, and they have access to everything they need. Now, the third decision you need to make is what the main agent would send back to the user. What the main agent sends back. What the main agent is going to send back. You need to make that decision also. You might just assume isn't not just the answer, it just sends the answer back, sends the whole report back. No, sometimes you can send other things. For example, you can, yes, we know you can send the final answer, so you just send the conclusion. You can send the conclusion of the sub agents. You can just send them to the user. Sometimes you want to also send the reasoning why it was so. So you can send the reasoning behind it. That's your result plus how the sub agent got there, how they got there. This happens when the main agent needs to validate why certain things are the way they are. So you would want to send the reasoning back to the user. And sometimes, for some reason, if you are probably running this multi-agent system within another system, you might want to send the full message history, everything the sub-agents did. You will want to send it back, because if you're working within another system or you are interacting with another API, full transparency is going to be needed. Full transparency is often going to be needed, and it also helps you to properly debug. You have all the data you need to debug the activities that happen. So that's another thing you need to decide. What do you want to send back? What are the things you want to send back? These are part of the things that you can put in the instructions, system instructions, or instructions of your create agent, and also defining your graphs. What do you want to send back to the user? So those are decisions that you need to make. Now that we've looked at all this, let us talk about benefits and trade-offs. Yeah, benefits and trade-offs. What benefits do we have using this pattern, and what are we foregoing or we need to be aware of? Caveats, some gotchas. Just going to put the title here. This will be benefits and trade-offs. Benefits and trade-offs. Let's fix this. Okay. So sub-agent pattern, what are the benefits and trade-offs of using this pattern? Let's start with benefits. So put benefits here. Keep writing benefits for some reason. Okay, benefits and trade-offs. Trade-offs. So benefits and trade-offs of this pattern. The first benefit, let's use large text here, is the clear separation of concerns. Clear separation of concerns. That's the very first benefit. So each subagent handles one domain and they handle it well. Their information is not bleeding into another agent, it's not causing confusion for another agent. Each agent gets what they need from the main agent, each subagent gets what they need from the main agent. They focus on their domain, they run their task, they do it well. So that's one thing. The second benefit is that you have centralized orchestration. Centralized orchestration. Because imagine as the CEO, you have to be the one dealing with the baker, dealing with the caterer, dealing with the design. That's a lot. It's better your HR takes care of it. So you just have to talk to your HR. Your HR gives you back the information. That's a whole lot less to have to deal with, a whole lot less chaos. So there's centralized orchestration. One place controls all the workflow decisions. If you want to find out where anything went wrong, decision-wise, orchestration-wise, routing-wise, is that guy. That guy is to account for it. That guy is to answer for it. You know specifically where to go to debug stuff. So that is another big advantage of this pattern. We've talked about context isolation. So just bringing that back, it is also a benefit. Context is well isolated between subagents. There's also parallel execution, which, while it is optional, it is possible. So anything that needs to be executed in parallel will be executed in parallel without getting any latency hits from that. So you can invoke multiple subagents simultaneously. Also, and this is for developer experience, your teams can work on different agents. So you have independent development. So you can You can dedicate different teams or even different people. It can just be Frank. Frank is responsible for the caterer agent. Linda is responsible for the decorator agent, and John is responsible for the baker agent. Yeah, so it can even just be a single developer per agent, and it can be teams depending on how big your development department is. So there's that. You also get easier testing. Easy is relative, but at least compared to some that we might be seeing later, or rather that we're going to be seeing later, it's easier to test. You can test your subagents in isolation, and you can also test them together in integration. So you can do unit tests and you can do integration tests for the entire multi-agent system. Then, just like the microservices architecture, which some people love to hate, it is scalable. It is scalable. And this is because you can add new subagents without changing existing ones. You can increase the capabilities of your subagents. You can better their prompts. You can better their tools. And you can just make them better in every way. And you can also remove. You can also do addition by subtraction. You can remove stuff just to make sure the system is good. All the while not disrupting the entire system. So that's another thing. We also have better tool selection. Better tool selection. Like I said in the beginning, especially when we're discussing multi-agent systems, when you give an agent just the tool it needs for a specific task, then it's going to make better decisions. It's going to make better decisions because each subagent has fewer tools, more relevant tools, so their decision is going to be razor sharp. So you have that. Then this might sound redundant, but there is modular maintenance. No, it's not redundant at all. Yeah, there's modular maintenance. It kind of ties into the development team thing, I think, the independent development. But yeah, modular maintenance. You can update each sub-agent without affecting others. Everything is modular. It's a modular system, and you can just take one sub-agent, improve it, or remove some tools, add some tools, and it will not affect others. So that's a very, very good thing to have. Now let us talk about trade-offs. What are the trade-offs? What should we be aware of? The first trade-off is definitely all the extra LLM calls. All the extra LLM calls, because so this is what happens. Your main agent makes a call and decides, yeah, I need to call this sub-agent. Then he calls that sub-agent, who also makes a call and does his task and returns the result to the main agent. Then the main agent has to still take that information and make a call, an LLM call, to make sense of it. So it's just added an extra LLM call. Just added an extra LLM call to it. So let's use diagram. We don't have so much space for diagram, but let's just use diagram. So this is your main agent. It calls. It makes an LLM call to determine that, yeah, I need to go to this particular subagent. Okay, cool. Go to the subagent. Go to the subagent. Now this subagent does his work. It makes his own call to do its work. Probably call some tools too, but yeah, just makes his own call to do the work. And that's the second call, the second LLM call. Then he returns back his result. Pull this up a little bit. Then returns back his result to the main guy. Returns back his result to the main guy. Now the main guy, instead of just passing the result in a single agent system, just passes the result, it still needs to make another LLM call to analyze what this guy got back. You need to make that extra LLM call. So there's an extra LLM call with every single sub agent that this main agent interacts with. So yeah, extra LLM calls are part of the overhead that you have to deal with. So you should have enough tokens to accommodate that. Because in this pattern, there's really no way to work around it. The only way to work around it is to accept it. Just accept the cost. Yeah. So next we have no direct user interaction. No direct user interaction. So the subagents, this has to do with subagents. The subagents can't ask the user for clarification. So for example, if the baker needs to probably just say make a red velvet cake and she was not giving specifications as to the width of the cake, she can't call the CEO. You can't call the CEO. No, you can't call the CEO. You have to call ask HR. Ask HR. So there's no direct interaction between the user and the subagent. So the subagent cannot directly ask the user for more clarification. Now, one way you can mitigate this is if you use human in the loop interrupt. You interrupt with an human in the loop call, then the user can provide more information, and that information goes directly to the subagent. Or another way is if the main agent asks. If the main agent asks, yeah, you can get that information and pass it to the subagent. Probably before the task gets to the subagent, the main agent realizes that, yeah, CEO, how big should the cake be? I don't want to bring a 3-layer cake and you'll be like, are we doing a wedding? The CEO is like, yeah, just a I think 3-inch or 4. Just make it this simple and all that. So the main agent gets all the information ahead before calling the subagent. So that's the only way you can mitigate this. Else, there's no other way. The subagents cannot interact with the user. Only the main agent can interact with the user. Also, like we discussed, subagents are stateless. Subagents are stateless. And while we have discussed the benefits of that, definitely there are also disadvantages to that. So they can't remember previous calls. And the best you can do is that the main agent will pass necessary context. Except from the conversation history, any other context from any other source, so that the sub-agent can use that to sure. Okay, let me go in this direction. So yeah, that's the only way you can mitigate that. Definitely increased latency because of all the back and forth. So increased latency because you have to get in this report back, forth, and all that. So yeah, for example, like you're trying to get paid. You're trying to get paid as the sub-agent. You're the baker. You're trying to get paid. You first have to submit an invoice to the HR. Then the HR has to submit it to the CEO. Then CEO has to approve. Then has to send it to the HR. Then the HR has to call the oh my god. But if you're just talking directly with the CEO, he might even pay you out of pocket. It can be that fast and direct. So yeah, increase latency. The only way you can mitigate any type of latency issue is to use parallelism where necessary, or where possible rather. Where possible, use that parallelism. Yeah, also where necessary, use parallelism. That's the only place you can mitigate the the latency bottlenecks. But you can't bypass the back and forth communication that has to go on between the main agent and the sub agent. Then all the extra calls will definitely give you higher costs because of all the tokens you'll be spending back and forth, or the back and forth communication between the main agent and the sub agent. More tokens are going to be processed. You also have to accept this cost. There's no mitigation strategy. You have to accept this cost, but it's worth it for complex orchestration. So there's always a cost budget to every type of direction you choose to go. There's no perfect pattern. There's no perfect system. Another thing is synthesis complexity. Your main agent should be smart enough to know how to synthesize the information from the different agents, or rather from the different sub-agents. It has to be smart enough to do this. LLMs are getting powerful these days, so they kind of know what to do if you give them good prompting, because that's the only mitigation. Strong synthesis prompting. You have to give them good prompting to make sure that they know what to do. They must combine all the results in a way that is not conflicting. For example, with the HR analogy, she might not be a cake expert, a catering expert, or a decor expert, but she has to have general knowledge about all these things. She has to have general knowledge about all these things. Else, will she go back to... You can't be asking your CEO some questions. So you have to take charge. You have to have agency over the sub-agents, and you have to make sure that you direct all those sub-agents, the caterer, the baker, in a way that all their activities flow. Everything can't just be scattered and all over the place. You're not doing your job well. Another thing is routing errors. And this would always happen when you have ambiguous prompts. Your main agent might go and call the wrong sub-agent. If you have ambiguous descriptions in your tool descriptions for the sub-agent, you remember you wrap them around the tool, or you have ambiguous prompt inside your sub-agent, your main agent is not going to know which guy does what. So you can't just say bakes cake, or just get stuff done. You can't give such kind of vague stuff. You have to properly define what the sub-agents do, have clear boundaries between what each person does. We should not say cake and you go and call a caterer. that will be catastrophic. So there should be clear boundaries between what they do, and this can be done through clear tool descriptions and very, very good prompting. You don't want to be calling the wrong guys or missing out some guys that you're supposed to call. So that's a very important step. So yeah, those are our benefits and trade-offs. Let's look at when to use this pattern. When do we use this pattern? New frame. Get this out of here. It's 200. 100, no, 100. So when do we use this pattern? When do we use the sub-agents pattern? Or when to use sub-agents? When to use sub-agents? When to use sub-agents? Now, we're going to be looking at this under two different headings, rather. So, when to use and common use cases. When to use and common use cases. So, when to use, first, when you have distinct specialist domains. When you have distinct specialist domains, you use sub-agents. It's kind of the argument to use multi-agent systems too, but yeah, definitely where sub-agents is a subset of sub-agents. So yeah, when you have distinct specialist domains, you want to use sub-agents. They're not, okay, I think what the better way to describe it is that when they're not dependent, when electrician, plumber, this thing, they are related. Not that they're not related, but they're not dependent. So they're distinct specialist domains. Then use sub-agents. Also, when subagents don't need to talk to the user. Don't need to talk to the user. So for example, in the HR example, the baker does not need to talk to the CEO. The caterer does not need to talk to the CEO. So definitely you need a coordinator to just coordinate all of them and get things done. So that's another aspect when you use subagents. You also use them when you need centralized control. Centralized control, you want someone to just handle it. So yeah, you want that. You want the context to be isolated. You want the context to be isolated. You need parallel execution. Not all the time, but when it's necessary. And you know why that is important later, because the subagents pattern is very close to the routing pattern, but the routing pattern parallelism is not an option. So, but for the subagents pattern, parallelism is an option. You can use it, you cannot use it. Only when it improves performance, then you use it. So, when you want different teams, part of the benefits, when you want different teams to own different agents, and different teams to own different agents, and also when you need clear separation for testing and maintenance. When you need clear separation for testing and maintenance, yeah, use it. So yeah, this is your rule of thumb to know when you need this pattern. To wrap things up, let us look at common use cases. Let's look at common use cases in the real world where this is used. First, personal assistant. Yeah, personal assistant. Get my flights booked, get my hotel reservations, get my script written for the talk I have to give. Yeah, personal assistant. You want to have a calendar agent, you want to have an email agent, you want to have a task agent, specialized agent for different things. Yeah, this is very amazing for a personal assistant. There's a course I'm going to be releasing soon, most likely after this one, where we get to build ChatGPT from scratch. And I'm seeing the subagents pattern as kind of like the best pattern for this, because all these chatbots are basically like personal assistants. So the chatbot gets to talk to you, but whenever you need to do any specialized thing, it will just use a subagent underneath. Do that, give you the result, but back and forth, you keep talking to the main agent, which is the chatbot. So yeah, personal assistant. Then we have research workflows. If you need to research different domains and synthesize information from all those different sources, yeah, this is perfect for it. You want an agent that finds information, an agent that analyzes, an agent that interprets. Your subagent's pattern can have the main agent doing the task sequentially, from researcher to analyst to writer. Another thing is customer data platforms. Customer data platforms. So you have a CRM agent, and we also have an analytics agent, a reporting agent, just different agents that specify on different customer domains. Also, if you want to do code generation, you can have an agent that specializes in planning, another that specializes in writing the actual code, another that reviews the code. So they all do it sequentially like that. You see, the subagents pattern is kind of like very, very flexible. It can work sequentially, it can work in parallel, in different ways. We're going to be seeing other patterns later that they're either sequential or they're either parallel. So just giving you that information ahead to see more reasons why you might want to use the subagents pattern for a use case that fits the attributes of this pattern. Also, definitely content creation. You want to have an agent that researches, another agent that takes the research, drafts an outline, and another agent that just writes and edits, or even an agent that publishes. So you can use that for content creation. So yeah, these are common use cases in the real world where you can use the subagents pattern. And yeah, that's all for the subagents pattern in this video. So in this video, we're going to be looking at another multi-agent pattern, and this is the hands-off pattern, the hands-off pattern. Now, I want to believe that if you're not living under a rock, you have seen a relay race. Yeah, you've seen a relay race, and you know how it works. You know how everything works. So, you're watching the Olympics or any athletics event, and you're watching this relay race, and you see the first runner, runner one. Say runner one. It's definitely too big, so let's just make it, yeah, or medium, yeah. So we have runner one, and she takes off. Runner one takes off, and when she's done completing her lane, she hands the baton to runner two. She hands the baton to runner two. Runner two takes off, completes her track, and she hands the baton to runner three. Runner three completes her part of the race and hands the baton to the final runner taking lane 4, who then completes the race. That should be great. Oh, yeah, good. So that's how a relay race works. Just in case you've not seen a relay race before, that's how a relay race works. So the first runner on lane 1, oh no, the first runner, yeah, the first runner can be on any lane, can be on any lane from lane 1 to lane 8. Has a baton, runs a particular part, and hands the baton to runner 2. Runner 2 takes over with the baton, runs our part, hands the baton to runner 3. Then runner 3 completes a part and hands the baton to runner 4, who then takes the last track and completes the race. This is basically how the hands-off pattern works. Yeah, this is basically how the hands-off pattern works. Probably not in a fixed order, but sequentially. And what happens is that you have one agent. Let me set all these colors back to being transparent because that will help my illustration, the one I'm about to give. So you have one agent that is the first agent that meets the user. This is the first agent that interacts with the user. This is the entry point agent. There has to be an entry point agent. So yeah, this is the entry point agent. Though all agents in this system are at the same level. There are no sub agents, there are no lower agents. They are all on the same hierarchy level. So the user interacts with this system and encounters the very first agent. Agent 1. And at that point, that agent is the active agent. It says, hello, how are you? This is and that. You just imagine like you meet a receptionist. Oh, hello, how are you? This and that and all that. Get your information and all that. And once they're done, once this agent is done with you, it then transfers you to the next stage of the task you're about to complete. Which will be done by another agent. Which is going to be done by another agent. And automatically, once that transfer is done, this becomes the active agent. Yeah. This is deselected as the active agent, and agent 2 becomes the next active agent. Just as in a relay race, once the first runner is done and hands over the baton to the second runner, he or she just stands. The second runner is the next active runner. She's the one that keeps blazing. He's the one that keeps going. When he's done, he hands over the baton. He's no longer the active runner. The one with the baton is now the active runner. And it goes on and on like that until the task is finally completed by the last agent, which is the final active agent. And at each point, the active agent is the one that is interacting with the user. The active agent is the one that is interacting with the user. So that's how the hands-off pattern works. That's how the hands-off pattern works. Unlike the sub-agents pattern, for this pattern, there's always an active agent. There's always an active agent. Amongst all the agents that are available in the system, there's always an active agent. And once the user interacts with that system, that active agent is the one that gets to interact with the user. That active agent can be a specialist in one thing or another. But I think to understand better, let us use a real-world system. Let's look at a real-world system where this type of thing can be implemented. So let us do customer service. Let's say this is a customer support system. This is a customer support system, a customer call center. So let's just label that. Let's say customer call center. Customer call center. So we have a customer call center. And in this customer call center, we have a general support agent. We have a general support agent. So general support. We have a general support agent. Then just copy this. We also have a billing agent. Billing agent. This is the agent that takes care of all billing issues. Good. We have a technical agent. Technical support. Let's call this billing support. So a billing support agent, a technical support agent, and a general support agent. So we have these three agents. You can have more. You can have more based on how many services this customer call center helps users with. So a user comes. Well, let me ditch this arrow. Let's not use an arrow. Let's just say user. So this is a user. Let's do this and say this is our user. So here we have our user. So the user comes to this customer call center. By default, the customer call center sets the first agent as the general support agent, the first active agent as the general support agent. So anytime you come to this customer call center, you first meet the general guy, the guy that has a little bit of knowledge about everything. So this is the agent that you encounter. Then when you reach this agent, you tell it, yeah, my credit card was double charged. My credit card was double charged for my subscription this month. Then the general support agent looks, yeah, okay, thank you for providing that information. You can also ask for some extra information like your name, your account info, and everything. Then internally, with knowledge of all the other agents available, it will realize that this particular issue can be handled or is to be handled by the billing support agent. It's to be handled by the billing support agent. So what does this agent do? It immediately updates the state to deselect itself as the active agent. It deselects itself as the active agent and updates the billing support as the active agent. It updates the billing support as the active agent. And once it does that, it then tells the user, it responds to the user by saying, let me transfer you to our billing department. Let me transfer you to our billing department. And from that point on, any request that the user sends is now going to the billing agent. Any query that the user makes is now going to the billing agent. The general support agent basically handed off to the billing agent. It handed off to the billing agent. And the billing agent takes care of it and it responds to the user and helps the user take care of their billing issue. It can then say something like, is there any other thing I can do for you? Let's assume the user then says, yeah, I noticed that I've been trying to log in for several days now, but I've been getting this particular error. What happens is that the billing agent is also smart enough and also has knowledge of all the agents available. It's smart enough to realize that this sounds like a technical problem. It sounds like a technical problem. So what does it do? It updates the state to deselect itself as the active agent and then selects the technical support agent as the active agent. It then replies the user by saying, let me transfer you to our technical specialist. And by the time the user sends a new message, the user is now speaking to the technical support agent. That's how hands-off works. Sometimes the general support can jump to technical support. It doesn't have to follow a specific order. It just hands off to the appropriate agent, and each agent can hand off to any other agent available in the system. If the user's technical issue is resolved and the user says something like, what are other services that you guys offer? This is not a billing issue, neither is it a technical issue. So the technical support agent already knows that this is not my burden to bear. And if there is no other agent that specifically handles that, it will just transfer control away from itself and back to general support. Because of course general support should know a thing or two about more services that the product offers. So the general support can then reply the user and guide the user on any other services that they can purchase to improve their experience. So that is how the hands-off pattern works. The key insight to this pattern is that only one agent talks to you all the time. At every single point in time, you are only speaking with one agent. Multiple agents are not being called. State is being updated to transfer control to the agent that is responsible for responding to your query. That's basically what is happening. So at every point, you're talking to one agent, and what is going on within the multi-agent system is that the agents here are transferring control to each other based on the user's query. How amazing is that? And this is exactly how the hands-off pattern works. Now, to further break things down, let us look at some of the key characteristics of this pattern. Let me get everything here. Let's shrink it down. I can put it here. And now let us discuss characteristics. So, let's look at key characteristics of this pattern. Characteristics. And the first is going to be, like text, distributed control. Distributed control. Now, in this pattern, as you have seen, there's no single supervisor. Nobody is supervising everybody. Yeah, nobody is supervising everybody. Of course, you have an entry point agent because you have to select one by default for the user to talk to first. But that particular agent is just at the same hierarchy as every other agent in the system. There's no central supervisor, and any agent can be active at any time. Any agent can be active at any time in this multi-agent system. So that's the first thing, distributed control. There's no centralized control. Secondly, there is direct user interaction with every agent. There's direct user interaction with every agent. So the user gets to talk to every agent. Unlike the sub-agent system where you only get to talk to the main agent, you don't get to talk to the sub-agents. Here, the user gets to talk to every single agent. So you get to give it your context directly, you get to give it your information directly, it chats with you directly, it asks its questions if it has follow-up questions, if it needs more information, it's going to ask the user directly and make sure that it satisfies the user directly. So direct user interaction with all the agents in the system. Also, there's explicit transfer of control. There's explicit transfer of control. There's no partial transfer of control. Once a particular agent is in control, it's in total control. It's in total control. Whatever it does with the user is at its own discretion. The agents between each other use two calls to transfer control from one agent to another. And once a particular agent is in control, it's in full control. Also, the transitions are highly stateful. Once you transfer control, the new agent gets all the context. It gets everything. State persists across agent switches. So if from general support, billing gets the new control, the entire state, the entire conversation history that happened with general support is going to go to billing. Later on, we're going to be seeing whether that's a good thing or a bad thing, but every agent sees the full state. So stateful transitions. The next characteristic is that the flow is always sequential. The flow is always sequential, and you will always talk to one agent at a time. You can't talk to two agents at a time. You can't do that. You will always talk to one agent at a time. Like I said, in some situations, that can be a good thing. In some situations, nah, not so much. But the flow is always sequential. You have one active agent at a time. When you need to talk to another agent, control is transferred to that agent. There's no parallelism. There's no parallelism in this particular agentic pattern. So, sequential flow. And because of stateful transitions, we have conversation continuity. Conversation continuity. So you can simply ask the billing support about anything that you discussed with the general support, as long as you're not trying to give it a task that has to do with general support. You can ask it, you can remember your name. You can remember the name you gave general support. You can remember the email address you gave general support. You can discuss some of the issues around your account with that agent. But when it needs to do a particular task and it realizes that it is not the one for it, it will transfer control to the agent that is to perform that particular task. So the conversation flows through. It's continuous. Full message history available to the receiving or active agent. So yeah, those are the characteristics. Now, how do you actually implement this type of pattern in LangGraph? We've been discussing a lot. Might be time to see some code. And I'm going to be introducing a familiar friend called the pseudocoder. Yeah, time to bring back the pseudocoder. So how do you implement this in LangGraph? There are actually two ways. First, you can use a single agent and dynamically switch its prompt and tools. Yeah, it can be that fancy. You can use a single agent. You can actually build this multi-agent system using a single agent. But you get to swap its tools and instructions, and by the time the user is conversing with it after the switch, it's like you're talking to a totally different agent. You're basically talking to a totally different agent, because what controls agents are their prompts and their tools. So that's one way that you can do that. And you can do your switching using the middleware parameter, because if you're going to be using a single agent, you have to use the create agent. You have to use the create agent model. I'm going to be doing your switching, but let us see how it's implemented. Let's see how it's implemented. So the first thing you have to do is to define your state. You first have to define your state. So let's define our state. We'll assume that we are creating this for the support agent that we described, or support multi-agent system. So we define our state. It inherits from agent state, which is the default state that goes into the create agent model. So we just create a new definition using a type dict, and we set a current step state variable that is a literal, which represents each of the agents: the warranty agent, the classification agent, and a resolution agent. Then, warranty status and issue type. You can set any variables you want based on the type of system that you want to build, but we're going to see how this makes sense later. So we're going to create our state. It will inherit from agent state. This allows you to pass custom state to your create agent model. So we then need a system, we need a mechanism to swap our prompt and tools. We need a mechanism to swap our prompt and tools, and that will be done by using the model swapping middleware. The model swapping middleware that we saw in the lesson on building single agent. This will be done with the wrap model call decorator, and we'll give it a function that is going to do that swapping for us. We create a function that helps us swap our system prompt and our tools. So what this does is that it gets the current step from the state, defaults to warranty, gets the current step, and this step config is going to be an object that contains all the tools and the prompts for our different agents. Each agent represented by the key of its name. So when you pass its name into this step config, this config is going to load its tools and its prompt, which you have defined in a dictionary. So once you load that, you then use request.override to override the system prompt, which you will set as the prompt coming from the config of that particular agent, and also you override the tools by setting it to be the tools from the config of that particular agent. So finally you return the handler with the request. So that's how you do your automatic swapping based on the state. That's how you do it based on the state. This is called whenever the user interacts with the agent. So once the user is interacting with the agent, you get the current state, and you get the current step, which the agent that is handing off has already updated to be the next agent, and that agent's configuration will be used to swap the system prompt and also the tools. And once you have this set up, you can then define your agent. With create agent. You give it your model, you give it your tools. Your state schema is going to be this support state that you have created, which is a custom state for this agent. And the middleware is going to be the middleware that reads the current step and applies the swapping of your system prompt and your tools. And then you add a checkpointer to maintain memory. That is very, very important. So yeah, this is one way by which you can create this hands-off multi-agent system. This is very fancy. You are using one agent and you are swapping its persona. You are swapping its behaviors at runtime. So that's one way. Let's look at another way you can do this. Now, the second way we're going to be looking at is the land graph traditional way, the bare bones way, where you get to use nodes and edges. Now, here the first thing you do is to define your agents. You define your separate agents. Let me put a comment here and say define. So you define your agents. And a quick way to define your agents is to just use create agent. Just use create agent to define each of your agents. You can still use a normal graph to build it up, but if it's going to be a React type of agent, if it's not a complex agent, if it's just an agent that uses the React pattern, just go ahead and use create agent. It's way easier and it's very, very powerful. So you define your separate agents, and the next thing you will do is to define a function that is going to read state and transfer to the next agent. It's just going to read state and know when to transfer to another agent. So to do that, we simply define our conditional routing function. It is route to agent. It reads the state. It reads current agent. We are assuming the previous state too, where we have current agent. It will read current agent, and current agent can be set to general, it can be set to billing, it can be set to technical, which are going to be the names that we're going to use to add these agents as nodes to our graph. And then once we have this function, we can create our handoff workflow. The workflow equals state graph, where we pass in support state. We add our nodes, which are our agents. We add each of our agents as a node. And then we add conditional edges. So our agent just starts and it goes to route to agent. And what route to agent will do is to simply return the current agent, which can either be general, billing, or technical. So let's say by default it's general. So from start, we'll go to the general agent. If you are conversing with the general agent and you have a billing issue, it will update this current agent state to billing. And then the next time the user talks to the multi-agent system, route to agent is going to route to the billing agent. If the billing agent also sees a technical issue, it will update the current agent state to technical. If it's a general issue, it will update the current agent state back to general. And the application is smart enough to go from start to whichever agent is currently the value of the current agent state variable. So yeah, these are the two ways that you can create the handoff flow within your multi-agent system. There are some other strategies that are available. For example, you can use tool calls, and inside the tool, you can simply use command to update the state and also redirect to the required node. But with these two strategies, you are good to go with your handoff implementation. Let's look at an example where we use a tool call to handoff. Just going to clear this, bring the pseudocoder down. And as I mentioned, you can do your handoff within a tool. So you write a tool. For example, this tool says transfer to billing. And one thing you can see with these tools is that they are very, very specific, even though you can make it dynamic by passing the particular tool you want to transfer to. But this one is very, very direct. It says transfer to billing. You get your reason in, which is the reason from the agent that is transferring the control. You get your tool runtime. You will then return a command. You then return a command object. You return your command object. Use your command object to update the state. First, you need to add a tool message to the messages list because you are actually calling a tool. So to make sure that the messages list is coherent and is consistent, you have to add a tool message. That's why we needed the runtime so that we can pass the tool call ID. You can also feed in the reason, which is very, very important. Then here you can update your current step to billing, and this would automatically trigger the handoff to billing, because the next time the user calls the agent, the billing agent is now the current step, and that is the agent that is going to be talking to the user. So yeah, they are basically the 3 steps. You can do the fancy one where you're shape-shifting a particular agent to take on different personas. You can use the graph workflow where you create your separate agent, add them as nodes, and you conditionally route to them based on state. And also you can just do a more explicit routing within a tool call. So yeah, that's how you implement the hands-off pattern. Now let us look at benefits and trade-offs. Look at benefits and trade-offs. Bump this up, and here are benefits, and we have trade-offs here. What are the benefits and trade-offs to this pattern? As usual, let's do benefits first. Let me go large. And the first benefit is that you have direct user interaction. Direct user interaction, meaning that the user can talk to any agent directly. Each of the specialist agents get to talk to the user directly. So they get to converse with the user directly, they get to get all the context, they get to ask their questions, they get to get everything they need from the user to perform their operation. They get it. Unlike the sub-agent pattern where everything has to go through the main agent. Also, you can have sequential enforcement. So you don't have a dynamic agent that is trying to decide who to go to. You can enforce that a particular criteria should be met before going to another agent. For example, if you meet the first agent and probably the first agent has to authenticate you, if you don't pass that authentication, that agent is not going to hand you off to the next agent. No, they're not going to hand you off to the next agent. So you can enforce do X before Y. Every do X before Y situation in your application within the multi-agent system, you can enforce it. It's within your control. Handoff is not going to be done until certain criteria is fulfilled. You have full control over that. Also, there's stateful context. And this is something that I see going in both columns. Benefits and trade-offs. There's stateful context, meaning that each agent has the full conversation history. They have the full conversation history. So they are following your customer journey. They are following in the support example that we looked at. Each agent is aware of your customer journey, so they can understand, yeah, this particular agent has talked to you about this, you've already discussed this, so they don't have to ask you again. They don't have to ask you some of the things that you've already provided. If you've already provided your email, they don't need to ask you again because they have the full information. Unlike when you have context isolation, if you have context isolation and you're talking to a new agent and that agent needs your email, it will ask again, even though it has been collected before, it will ask again, and you don't want that kind of hassle. So yeah, stateful context. But like I said, this is something that I see going in both columns. Another thing is natural conversations, which is kind of like a subset of the first one. Natural conversations, meaning that each agent can talk to the user in natural language. Each agent can talk to the user in natural language, and that kind of helps the user experience. The user feels like they are talking to different specialists because they get to have natural language conversations with each specialist. It's not like one guy taking your order and just goes away, and your experience is dependent on how well that person interprets your situation or your order to the person that is actually going to carry it out. So with handoffs, you get to talk to the actors directly. Each actor, you get to talk to them directly. Another thing is flexible navigation. And what this means is that the handoffs can go back and forth as much as possible. You can go back and forth. You can go from the general support agent to the billing support agent. You can go back. Yeah, you can actually go back. You can go back to the general support agent. You can go to the technical guy, then back to billing, then back to technical. You can hand off as much as you want based on the problems you are trying to solve. Because sometimes you can come and, so when you get hold of support, you want to solve as many problems as possible. So probably you came because of a particular billing issue, but then they ask you, what else can I do for you? Oh, yeah, of course, you can do a lot for me. You can do this, and each responsibility can lead to handoff back and forth between the different agents. So you can go back and forth as much as possible. And this is also something that can be a problem. But yeah, for now we're talking about benefits, so let us stick to that. Another thing is clear responsibilities. Clear responsibilities. Each step is focused on one purpose. Which is kind of like a general benefit of using multi-agent systems. There's focus. There's that focus. That's one thing you get from all these patterns. And also, easier debugging. This is contextual though. Easier debugging of state transitions. Because the state transitions are explicit and traceable. They're very explicit and traceable. So yeah, easier debugging. Not easier debugging of state itself, as we're going to see later on. But yeah, easier debugging of you know when responsibility was handed off to this particular agent, so you know who did this. Then you know when the responsibility was added to this other agent. You can see the back and forth. You can time travel through the entire conversation process. Yeah, that's something that is going to help when you're trying to debug issues. So those are your benefits. Now let us look at some trade-offs. First, no parallelism. There's no way you can get parallelism to work in this pattern. You can't do it. Only one agent is active at a time. Now, if you want to, get really complex, each of these agents can use the sub-agent pattern. Yeah, you can actually embed these patterns into each other. Each of the agents that are being interacted with can actually be using the sub-agent pattern. So each of them can be a multi-agent system themselves. So you have a multi-agent system inside a multi-agent system. So each of them can be a multi-agent system because they might need to call sub-agents to take care of stuff. For example, technical guys might need to call the server guys if it's a server issue. They might need to call the code guys, the developers, for a code issue. They might need to call the DevOps guys for CI issues and stuff like that. So yeah, you can actually embed patterns inside patterns. So you can get some sort of parallelism inside that. Even you can embed a router pattern inside that we're going to be looking at later. You can embed a router pattern inside that can do some things in parallel. But just on the flat level, there's no parallelism in handoffs. You are talking to one agent at a time. Whether the agent is a multi-agent system on its own, that is up to you to know how complex you want your system to get. But you are talking to one agent at a time. There's no parallelism. The second thing is sequential latency. And what this means is that one step must be done before another step. Yeah. One step must be done before another step. That's why you can enforce, you can have sequential enforcement. One step has to be done before another step. Is also the whole no parallelism thing. So you have to face the latency that comes with sequential processes. There's nothing that is going to be asynchronous. Everything is all going to be done synchronously. So that's another thing. Another trade-off is that there will be context accumulation. So the context is going to continue to build up. It's going to continue to build up because each agent is taking the whole context. So every time you are stuffing the entire conversation history into each agent's context window. Every time you need to hand off, anytime you hand off to a particular agent, you are stuffing the entire conversation history into that particular agent. So yeah, that is going to be a lot of bloat. So you have to find a way to manage this. You can use summarization techniques. There are ways you can do map reduce techniques or some summarization techniques that LangGraph offers to be able to compress the memory in a way that it still remembers, but the token size, the token amount is not as much as feeding in the whole thing. So that's another trade-off that you have to be aware of. Another thing is the handoff overhead. Everything requires a ton. Every transfer requires a ton. Because for you to actually see the impact of the transfer, you have to prompt the system. That's when the system will say, oh yeah, I am now the billing agent, so you can talk to me about billing issues. When the transfer is done, it will just tell you that, yeah, you are being transferred. It's not like that agent is going to automatically start taking up the thing. No, you have to actually tell it your issue. Then it will then, yeah, I am the technical agent now. I'm the one in charge of your case. so I can do what you just asked me to do. So there's that part too. Also, you are going to face complexity due to non-linear workflows. You're going to face complexity due to non-linear workflows. Yeah, all those back and forth is going to be a lot of complex states to manage. That's why I told you that this flexible navigation and all that, yeah, it comes with its own baggage. So when it comes to debugging, when it comes to managing states, when it comes to all the going back and forth, you have to manage all that. You know that complexity is coming, and you have to know how to properly interpret your state. So you're aware of that. The Handoffs pattern is basically a state machine, so there's going to be a lot of state management complexity. Lastly, user experience. And why I put this here is because the users will notice all these transfers. They will notice all the transfers, and it just feels like you're just hopping them back and forth. Like, can't you just do the whole thing? Aren't you like an agent? Just get everything done. What's all this? Transfer me to the billing department. Transfer me to technical. Transfer me to this. It kind of feels bureaucratic. So, it can have its own like downsides when it comes to user experience. Some will not care. A bunch of guys will not care, but some will care. Some will care. So that's just something to be aware of. So yeah, those are the benefits and trade-offs we're going to be discussing. Let us wrap things off by discussing use cases. Let me get all this. Minimize this. Trade-offs. Let's wrap up by discussing use cases. What are the example use cases that this pattern fits like a glove? The first use case, as we have seen clearly and we have spoken a lot about, is customer support. I will now transfer you to marketing. I will now transfer you to billing. Yeah, customer support is a very common use case. Natural transfer between departments works seamlessly. Second, when you have multi-step forms. Users don't like filling long forms, so you want to break them down. So let's say the first agent is collecting general information. Then to collect the information, it also has the ability to validate it. Because of this pattern, you can also validate it. Then it moves you to the next section, contact information. Then that's another agent collecting contact information. Then moves you to another one, job experience agent collecting your job history, job information, and portfolio and all that. So yeah, multi-step forms are another strong use case. Similar to that are also onboarding flows. You want to onboard a new user, perfect system to use. It will guide user through steps, and they most likely will even know that they are talking to different agents. So it helps you to kind of organize everything into steps, and it helps different agents to be focused on each step. Another one, which we may have seen, is approval workflows. So for each step, you do one thing, there's an approval step, then if it's good, it will hand you off to the next step. Do another thing, there's an approval step, it's approved, move on to the next step. No other. Interview bots. I know people are divided on what they feel about interview bots, but yeah, that's something you can also use it to implement. I don't think anybody is going to be. I don't think people really complain about interview bots if it's true chat. Yeah, everybody understands that you can use that. But I think the one that people have most problem about is the visual ones, the one that actually use a bot to interview you with voice and speech and sometimes weirdly video. So yeah, interview bots where you have different topics requiring different expertise. For example, let's say the first bot just asks you about, just tries to know you, get your general information. Then the second bot is the technical bot that gives you like technical questions to answer. You get through that. Then there's a personality bot that does the whole personality interview and stuff like that. So yeah, that works too. Lastly, on our list is sales funnels. So you can use the hands-off pattern to simulate a sales funnel where you have qualified leads. Then from qualification you take them into a demo. Another agent takes care of giving them a demo. And once everything looks good from the demo, there will be another agent that's going to be your closer. Yeah, your closer agent. And it's going to try its best to make sure that it closes the client, it gets the deal, and marks it as a conversion. So yeah, these are use cases that you can use this hands-off pattern for. And that's the hands-off multi-agent pattern. In this video, we're going to be discussing another multi-agent design pattern. And that's the skill pattern. That's the skills pattern. Skills. Now, ever seen a Swiss Army knife? Yeah, like the one you're looking at on the screen. This is a single tool. A single tool, but with different implementations. Different implementations. They all cut, but you can pull out any one of them based on what you want to cut. This is scissors-like. This looks like something with a jagged teeth, so any saw-like requirements. This is a perfect knife. This looks like a knife that can get into corners and make like deep cuts. This just looks like it can file nails and stuff like that. So it's a single tool, a knife. It even has a screwdriver here and another type of knife implementation here. A single tool with different skills. Just like if you have a fighter, their main responsibility is to fight, but they can punch, they can kick, they can probably like do a headbutt, do some acrobatics and stuff like that. Those are their skills. And that's what the skills multi-agent pattern is all about. It's a multi-agent architecture where a single agent, note, a single agent, is a multi-agent architecture, but it uses a single agent. A single agent dynamically loads specialized instructions and tools based on what the task at hand is about. Now, you might want to ask, isn't this like the hands-off pattern we did with the fancy create agent model that we were swapping prompts and tools? Isn't that the same? In a way, but a skills pattern is not trying to do some sort of sequential stuff. It's just performing a single task and finishing it. There's nothing like handoff. You ask for one thing, it loads the skills for that thing, does it, and it's done. You ask for another thing, loads the skill to perform that thing, and it's done. So instead of having multiple separate agents, you have this one agent. I would call it a G.I. Joe. You have this one agent, and that agent can unlock different capabilities. Just like a fighter, if you need it to kick, it kicks. If it needs to kick, it will kick. If it needs to punch, it will punch. And all sort of stuff. So that is what the skills pattern is all about. But let us look at an analogy that is closer to something we can implement. Let's put our Swiss Army knife on one side. And let's say you have a skilled contractor. You hire a skilled contractor, a general contractor to renovate your house. Yeah, back to the renovation analogy. So you hire this general contractor to renovate your house. Now, this contractor, Frank, I said this Frank. Let's get Frank on the screen. So here is Frank, who is a general contractor, and Frank is multi-talented. Frank went to technical school, he knows plumbing, he knows electrical work, he knows how to fix floors, he knows upholstery, he even knows how to do POP. So, you have Frank, multi-skilled. This is Frank's knowledge base. This is Frank's knowledge base. Or, let's say, this is Frank's skill set. These are all the skill sets he got from school. He has plumbing knowledge. He has plumbing skills. Rather, Frank can also do electrical work. Frank also knows upholstery. So if you need to fix your chairs, if you need to fix the material on your chairs, yeah, you can do that. So Frank has all these skills. Plumbing, electricals, upholstery. Frank is so good. Or let's even call this generally carpentry. Carpentry. So these are Frank's skills. All these are Frank's skills. So you bring Frank to your house and you tell Frank, yeah, I need to fix some of the broken sockets in my house. I need to fix some of the broken sockets. I need to replace the power box. And I need to also install some lights outside. So what does Frank do? So this is you, the user, or the client, telling Frank that you need to do all those stuff. You need to replace the power box, you need to fix some broken switches, and you need to install lights outside. So what does Frank do after hearing those instructions? Frank is simply going to load in his electrical skills. Frank is going to load in his electrical skills. He's going to load them into memory and satisfy your query. He's going to get to work and he's going to do all that electrical work. He's going to do all that electrical work. Then once it's done, it gives you a response. It's done and you satisfy everything looks fine. You ask your back and forth questions, it makes his fixes and all that, all good. Then you tell him that you need some plumbing done. So what does Frank do? Frank immediately unloads the electrical skill, pick up the plumbing skill, and he loads it into memory. And then you guys can have a conversation about everything you want to do, and he's simply going to satisfy those requests. And it goes on and on. The same thing for carpentry stuff or upholstery stuff. You want to fix your floors and all that. Even if you need to go back to electrical stuff, it will load in his electrical knowledge and satisfy those things. Then you need some plumbing done again. It's going to load his plumbing knowledge and satisfy those things. So he will be loading the skills on an as-needed basis. Frank will be loading the skills on an as-needed basis. The same person, just accessing different expertise as needed. That's how skills work. That's how the skills pattern works. One agent, multiple skill sets loaded on demand. But how does this work in terms of implementation? How does this work in the land graph context? So, first, your agent is going to have some base skills. And the base skills are basically going to be basic instructions. Probably Frank just has basic instructions about the structure of a house, how everything fits together. It just has those basic instructions. So there is a base instruction that comes with the agent. And also a skill discovery tool. So what I'm going to do now is that I'm just going to extend this. And let's put another box here. It's going to be transparent. And this will be a skill discovery tool. Discovery tool. So it comes with base instructions, just basic understanding. Then it comes with a skills discovery tool. Let's call it skills discovery tool. Yeah, skills discovery tool. Comes with a skills discovery tool. It comes with that. So a user then makes a request. So the agent, with its understanding, is going to call the skills discovery tool. It's going to take the user's instructions, use his base instructions, and the skill discovery tool to get all the skills. It then identifies which skill is relevant to the user's request. Let's say plumbing. Which skill is relevant to the user's request? Oh, it's plumbing. It then uses a function, let's say like a use skill function, to load in that plumbing skill. It loads in that plumbing skill, and it also loads in instructions, because these skill sets, they're basically composed, as we're going to see later, they're basically composed of instructions and tools. So it loads in instructions and tools and other context, retrieve data and all that for that particular skill. It loads it in, and they are injected into context. The agent then takes the skill, uses it to fulfill the query, and the skills will remain loaded for follow-up instructions. If the user needs to say any other thing, why is this power box here? Have you replaced all the fuse? There seems to be a broken connection here. This switch is not working properly. It just maintains it. It maintains the skill for follow-up questions. And later on, for other subsequent queries, you can always unload the skill and inject new skills based on subsequent specialized tasks that the user wants you to perform. By the way, let me get rid of this arrow so it's not confusing. So based on subsequent specialized tasks that the user wants you to perform, new skills can be loaded. Let me put some arrows here. I'm going to put a direct arrow for plumbing. Then let's put a dashed arrow for others. So you can show that, this can also be loaded in. So this is basically how the skills pattern works. You load skills on demand. Now, before we see some pseudocode to see how the implementation looks like in LangGraph, let us look at some key characteristics. I'm just going to put the characteristics up here. Say characteristics. And the first thing is that this is a single agent. It's a multi-agent system, but it uses a single agent because you have a single agent that shapeshifts. Yeah, a single agent that shapeshifts. This is mystique of X-Men. So a single agent gets to shapeshift. It handles everything by loading skills on demand. And I think the Anthropic team mentioned that that's how Claude Code works. That's how Claude Code works. And that's why you can also write skills and feed it into Claude Code. And even most of these other agentic tools nowadays, Open Code and the rest, I was tinkering around Open Code the other day. They all have skills. You can load skills and give the agent capabilities on demand. So single agent, that's the first thing. One agent handles everything. On-demand loading, we've talked about that. Skills are loaded on demand. Also, additive context. Additive context. Like I said, the agent comes with a base set of instructions and a skill discovery tool. Then you can add on to that. You can use that to know the tool to load the tool. So that adds to the context of the agent. So additive context. Skills add to. They don't replace. They add to the base instructions. Another thing is that you need a tool discovery system. There has to be a tool discovery system. Or more specifically, let us say skills discovery system. Skills discovery system. So the agent has to be able to discover available skills and select the appropriate ones. That's what this tool is meant for. It has to be able to select the appropriate skill for the job and also know which skills are available. Also, there is weak isolation because context is going to be added up. All skills are going to share the same context window. So you really don't get that clean isolation that patterns like sub-agents have. One good thing is that you have low overhead in terms of communication. Low communication overhead. You have low overhead. So you don't have multi-agent systems talking to each other. You don't have all those inter-agent communication. You don't have to build a whole communication bus for agents to communicate with one another. You don't have to report back to a particular agent. You don't have to do transfer and stuff like that. So there's low communication overhead. These are the characteristics of the skills pattern. Now let us look at how we can implement skills in LangGraph. We're going to be bringing our pseudocoder in once again to see how this skill system works in LangGraph. First, let us look at what comprises of a skill. What comprises of a skill? Let me see if I can highlight all this. Yeah, all this. Reduce it. Yeah, let's put it here. Oh yeah, skill sets. Yeah, skill sets. Yeah. So a skill comprises of three main things. Skill composition. Skill comprises of three main things. First, we have instructions. So when building up your skills, you have to provide instructions about the skill. What it's all about. What does it do? Then your skill has to have a set of tools. What are the tools that the skill is going to use to perform the actual actions it needs to perform? For example, a database skill needs to be able to execute SQL statements, list tables, describe tables, and stuff like that. That's important. Then you have to provide metadata for your skill. These are things like name of the skill, description of the skill, when to use the skill, and many more, and even other contexts that the skill would need. The metadata is where you stuff in all that information. So yeah, these are three core things that has to be in your skills package. Now let us look at the sample implementation using our pseudocoder. Sample implementation, get rid of this, is a new instance of pseudocoder. And the first thing you will need to do is define a bunch of skills. So here we have a skills constant, which is set to a dictionary, and it consists of two skills. The SQL query skill and the data visualization skill. These are the two skills we have in this example. Inside SQL query, we have a description, which is part of the metadata. We have instructions, which are, we've talked about, they are one of the core things that has to be there. Instructions, how the skill is to operate. You are now equipped to work with SQL databases, guidelines, always use parameterized queries to prevent SQL injection, limit results to 100 rows unless specified, explain query logic before executing. So they are kind of like sub-instructions within that can feed into a main instructions. They're like sub-instructions that can feed into that base overall instruction set. Then you have the tools. You have the tools that this skill can use. Execute SQL, list tables, describe table. These skills have to be available to the agent when you create it. So, same goes for the data visualization tool. You have the description, you have instructions, you have a set of tools that it can use. So once you have your skills defined, you can then define tools that are going to help you discover your skills and use them. So here we have get skills, and what it does is that it lists all the available skills and their descriptions. Whenever your agent is being prompted, this is going to be called. So it's going to check and see all the skills available to it. So you just give it a list of your skills, and you can know, I have this particular skill, I have this particular skill, I have the particular skill, and this person is requesting for a database operation, so I should be calling the database query skill. So it uses that to determine which skills are available. Then it then takes the skill it wants to use, calls this particular function. This function is a use skill function that you create so that it can take in a skill name and load the skill. Takes in a skill name and loads the skill. So with the skill name, you can go first check if that skill is available in your skill set. If not, you say that it's not available. If it's available, you get the skill, and then you can return the skill. You can return the skill into context. And then with these returned instructions, the agent will know that, I now have access to these instructions from this skill, and I have access to this skill. I have access to its instructions under the skill instructions, and I now have access to this list of tools, which it will definitely recognize from its tools list. That's the one that was provided to the agent upon creation. Now, sometimes you might want to add your skills dynamically. You don't want to provide all the skills at once to the agent when you define it. To do that, you can write a function like this. This is not formatting well in pseudocoder, so I'm just going to open another instance of it. So you can write a function like this. Write a function like this, which is going to be a middleware that is going to interject your model definition and be able to load skills on demand. So you can have all the skills defined as functions. You can have them all in a module file, all defined. So this way, you can write this type of function, inject skills tools. What it does is that it checks for loaded skills. It checks for loaded skills in state. This is a state variable that tracks all the skills that you've loaded. So you then check if your skill name is already in the skills that have been loaded. If so, then you also check if that skill name is in skills. You can extend it with the tools available in that skill name. And once you get those tools, you can then, first, you check if there's any tool at all. Then you take all the tools that are currently available to you, all the skills that are currently loaded, then you add the new skills to it. You add the new skills to it. You can then override your model definition by setting your tools property to this new all tools that has been updated with the tools that are coming from this new skill that you just loaded. Then always remember to return your handler with the request object. So this is how you can load your tools dynamically. If you don't want to load like 100 tools at the beginning because you have like, let's say 10 skills and each of them have 10 tools. If you don't want to load all those tools at the beginning, you can load them dynamically when you're actually loading the skill that has those tools. So that's how you can make your code cleaner by loading tools dynamically. Tools for your skills, you load them dynamically instead of loading them upfront. Now let's go back to our whiteboard, and now let us look at benefits and trade-offs. Let's look at benefits and trade-offs. So here we have benefits and trade-offs here. So first, let us look at benefits. The first benefit is simplicity. Simplicity. You have just one agent. No intelligent coordination, no communication bus, no hands-off and all that. You just have one agent, just loading skills. Just loading skills based on the user's request, based on what the user wants it to be. A shape-shifting agent. Secondly, we have low latency. Low latency. No routing overhead between agents. You don't have to move around like the sub-agents. You don't have to move around like handoffs. Single agent is managing everything and loading skills as necessary. Next is flexible composition. Flexible composition. You can simply load multiple skills simultaneously. So if you have a particular task that has it juggling around the knowledge base and tools of plumbing and electric work, you can load them, compose them together, and you don't need to do any complicated agentic gymnastics to get that to work. So that's another thing. Easy to extend, easy extension. Easy extension. This way, you can add new skills without restructuring. If you want it to be more powerful, if you want to give it newer capabilities, just add a new skill. Just add a new skill. And that's all. Just add a new skill. It will discover it by itself. It will use it as necessary. Yeah, easy to extend. Another thing is shared context. Just like handoffs, there's shared context. So all the skills can see the full conversation. So if they need to refer to anything, for example, the handyman that is doing both electricals and plumbing, these are things that can clash within the walls. So it knows, it has context. It knows that, yeah, I laid these pipes here for some wires. Definitely, I shouldn't have any kind of plumbing going close to it. So yeah, shared context. Another thing is that there's a natural flow. There's a natural flow with the user. Everything seems like one conversation. Everything seems like one conversation. Unlike handoffs where you're like, yeah, I will now be transferring you to the marketing department, or yeah, I will now be transferring you to the technical department. This one just feels like a single conversation. It just feels like a single conversation. It's just one agent being a chameleon. There's no handoffs, so just basically feels like you're talking to the same guy. Also, it is cost efficient. It's cost efficient. You're using one agent, you're using one context window. You don't have to make multiple calls, make additional calls because you're trying to do communication. So yeah, it saves you on tokens. And finally, debugging trace is easier because single execution path to trace. Is a single execution path to trace. You don't have to trace multiple agents doing multiple things, and you're just tracing one single agent that is loading different capabilities. So yeah, those are the benefits. Now let's talk about trade-offs. First, you have the context window pressure. There's a lot of pressure on the context window to be very, very context aware, to be able to understand when it's to use plumbing, when it's to use electricals, when it's to combine both and everything. Loaded skills consume tokens and they mix a lot of information together. So you have to have a very intelligent model that knows how to do what is right when appropriate. Thank God models are getting smarter, but then you're still going to have to consume a lot of tokens because all the conversation history is being passed in. So context window pressure. Then we also have weak isolation. The plumbing work is not really separated from the electrical work, so a lot of that knowledge is coming and that can be confusing. Your skills must not have conflicting instructions. If your skills have instructions that overlap, if they overlap in a way that is conflicting, things are going to become very, very ugly. So that's another problem that you need to fix. Also, no parallelism. Yeah, your G.I. Joe handyman cannot do two things at once. Yeah, it cannot be doing electrical work and plumbing work at the same time. It cannot be doing them simultaneously. So you can't run skills simultaneously. Yeah, they can only feed off each other's context. When they're actually working, only one of them is being used. Also, you run the risk of having tool overload. You have the risk of running tool overload. We looked at the subagents pattern, and there we see that one of the main things is that it's able to help us split the tools. This guy does it too, but because everything is loaded additively into context, you have to have a very good unloading strategy to make sure that you don't load too many skills. You don't load too many skills and you don't load too many tools, because once you start having too many skills, you start having too many tools, and that will always lead to poor tool selection. So make sure that you have your unloading strategy in place. Next, prompt complexity. Base prompt is added onto the skills prompt, so you have to make sure that there's some sort of agreement between them. There's some sort of contract that you're maintaining. You have to always make sure that all the prompts get along. The base prompt, all the skills prompts, they must always get along. And even with that, this can start growing, and we know what too much context can cause to an agent. So that's always a problem that you have to keep in mind. Also, no specialization. It's just one dude that can do everything. And yeah, you can do your best to define your skills very, very well. But you can use different models. Of course, you might do the whole swapping of models thing. That's something you can do. But most of the time, you will be using the same model for all domains, and you might not be able to use specialized models for different types of tasks. So yeah, these are another caveats to using this design pattern for your multi-agent system. But I feel the model swapping middleware should be able to help in a way with this. But the problem is when you swap a particular model, you have to return all the contexts. So you probably are switching context window at that point, and yeah, that can come with its own complexity. So yeah, trade-offs and benefits, and I'm resizing them now because it's time to talk about use cases. So those are your trade-offs and benefits. Know how to make your decisions. So now let us discuss use cases. Use cases. And the first use case that this is awesome for is coding assistants. Coding assistants. Like I've said, Cloud Code, Open Code. Yeah. This pattern is amazing for them. You can load specific language skills. You can load skills for Python. You can load skills for SQL. You can load skills for JavaScript. So the skills pattern shines a lot when you are using it for this type of agentic implementation. Another thing is knowledge bases. If you want to be multi-talented, you want to be a polyglot, and you need to switch knowledge bases, yep, you can use it to load different domain expertise on demand. Another thing is document processing. In document processing. Now, take note, when I say use cases, it doesn't mean that this pattern can only be used for this particular use case. It's just that it fits that particular use case. Sometimes it doesn't fit the overall use case. It fits a particular problem within that use case. So keep that in mind. Like, for example, in document processes, it's easy for you to load different skills to process different files. If you're going to be working with different types of files, you can load in different skills to work on different types of files. We also have data analysis. In data analysis, you can have different set of skills that you can combine. You can combine querying skills with visualization skills with interpretation skills. So you can load them in based on what the task you want to perform. If it needs 2 of those skills, you load it in. If you need 3 of those skills, you load it in. Then you just switch from one skill to another based on what you are doing at the moment. It will always use one skill every single time, but at least it makes it multi-talented and it can do different things. It can query, it can visualize, and it can also interpret. Also, writing assistants. Writing assistants. And in this use case, you can use it to load different tone skills. You can load a formal agent, you can load a casual agent, and you can load a very technical agent. So that's one of the things. If you're a writer, if you're writing a writing assistant, you can load different skills based on the type of tone you want to write the document in. Also in DevOps automation. Interesting. DevOps automation. Here you can have a DevOps agent, a DevOps multi-agent that can work on AWS, can also work on Azure, or work on GCP, Google Cloud Platform. So you can load in different skills based on where the client would like to host their resources or manage their resources, the cloud platform they choose to use. If you want AWS, you load your AWS skills. If you want Azure, you load your Azure skills. So those are the use cases, and that will be all on the skills pattern. So in this video, we're going to be discussing the final multi-agent pattern, the router pattern, or the routing pattern. Now imagine you have a research coordinator. You have a research coordinator. Yeah. So let's do this. This is our research coordinator. Research coordinator. With the medium text. So we have our research coordinator. And we give our research coordinator a question. We give the research coordinator a question. So the research coordinator then takes that question, identifies which experts need to be consulted. Which experts need to be consulted. Let's say we need to consult an archaeologist. Would you consult an archaeologist? We also need to consult a geologist. And we also need to consult a meteorologist. All that topic has to do with fossils and stuff like that. Meteorologists. Yeah, I think I'm correct. Yeah, so we need to consult an archaeologist, a geologist, and a meteorologist. So the research coordinator identifies that. It then it breaks the tasks down based on what each expert needs to work on. It then sends tasks to each researcher in parallel. It sends tasks to each researcher in parallel. Then each researcher does their work, and all their findings is then synthesized into a final report. Probably they discover that, yeah, that bone belongs to an alien. Something of that sort. So they synthesize report. So they synthesize all that information into a report. This is how the routing pattern works. Yeah, that's the routing pattern. You can go home now. This is how the routing pattern works. The routing pattern is basically a multi-agent architecture where a classification step, not an agent, and this is very important, not an agent, a classification step analyzes the input. So we have an input here. We found some bones and we want to know what they're about. It analyzes the input. It then breaks it down into subtasks. Task 1, task 2, task 3. It breaks it down into subtasks. Or that's done here actually. It breaks it down into subtasks. It then identifies the agents that are to work on it and in parallel distributes that work to the agents. So take your part, take your part, take your part. So it breaks it down. This is the archaeologist's work. This is the geologist's work. This is the meteorologist's work. So give the archaeologist's work to the archaeologist, give the geologist's work to the geologist, and give the meteorologist's work to the meteorologist. So it dispatches these tasks to specialized agents in parallel. Everyone works on it, and the system synthesizes the final report into a unified response. It synthesizes all the results into a final response. This is how the routing pattern works. It is optimized for queries that benefit from consulting multiple knowledge sources simultaneously. That's your use case right there. Any situation that benefits from consulting multiple knowledge sources simultaneously, running multiple tasks simultaneously, the routing pattern fits perfectly. The routing pattern is designed to work in parallel. It's designed to work in parallel. So if you just have one shot stuff, don't bring it there. If your stuff are going to be one shot, you only need to consult one agent, do something in sequence. No, that's not what we're doing here. We don't do that here. Parallel work. Parallel work is the main selling point and strong point for the routing pattern. For example, let's say you bring a paper or you bring a question, not a paper, that asks, what are the economic, environmental, and social impacts of electric vehicles? The research coordinator is going to analyze that and break it down into 3 parts. 1 to economics, 1 to environmental science, 1 to sociology. All of them work in parallel. It will then synthesize all the results and provide the final report. So based on your question, is broken down. It can be broken down into 4 parts. It can be broken down into 5 parts. It can be broken down into 7 parts. And agents, specialized agents, are going to be spun up simultaneously to work on them and to give you a final synthesized result. The key insight here is parallel dispatch to specialists, synthesis of results. Keep that in mind. Parallel dispatch to specialists and synthesis of results. Now let us look at some characteristics of this design pattern. We come here, and I think I should be able to stick the characteristics around here. Let's do our asterisk characteristics, asterisk and obelix. So characteristics. First, it always has a classification step first. So it always runs a classification step first. Not a classification agent, a classification step. So you have a classification step. This is where the router is going to analyze and decompose your query so that I can identify the different parts and the different agents that are to work on it. Also, like I said, it is fully and permanently designed for parallel execution. Multiple agents get to work simultaneously. They get to work in parallel. And also, each agent receives a targeted piece of the puzzle. Targeted in the sense that it is according to their specialty. Each agent gets a domain-specific query. So the classification step is going to do the breakdown and package a very detailed instruction, domain-specific, to a particular specialist agent. So it's going to package that. It can be for 3 agents, it can be for 2 agents, it can be for 5 agents, depending on the number of specialists it has identified to work on that particular task. Next, we have selective routing. Now, for example, these are not the only experts that the research coordinator would have in the department. These are not the only experts. There can also be a paleontologist. There can also be a biological scientist. There can even be someone that specializes in metal works. But based on the task it was given and the breakdown it did, it would only call the guys that should be involved. It will only invoke relevant agents. So even if you have like 15 agents in this system, only the relevant ones are going to be called. Only the ones that are relevant to the task at hand are going to be called. It's also similar to the sub-agents where you only call the agents that you need, but these ones will always operate in parallel, unlike in sub-agents that you can actually have them working sequentially. Also, we have result synthesis. Result synthesis. There is a synthesization step. I hope I'm calling that correctly. Synthesization. Okay? There's a synthesis step. So that's where all the results are combined into one unified response. So every result from all the sub-agents is collated, and that response is handed over to the user. Now, this is also done statelessly. So the operation is typically stateless. The agents only receive what they need, and each of the requests is going to be handled independently. No context from any other guy. The archaeologist is going to do his work, walled away from the geologist, who is also separated away from the meteorologist, and definitely the archaeologist too. Everybody gets to do their own work independently. Then the system, the harness, is going to synthesize everything and pass the final result. And you may have guessed, there's definitely context isolation with that. So context isolation is also one of the characteristics of this pattern. So classification first, there's always a classification step first. Parallel execution. The execution is always parallel. If you are doing one short stuff, don't come here. It's always parallel. We need to spin up 2, 3, 4, 5 agents. Then the subtasks are targeted at the specialists. Selected routing, or selective routing, rather, not selected routing, sorry about that. So there's selective routing. So we only select guys that we need. We don't need everybody. We only select guys that we need. Result synthesis, that's the final step before a response then goes to the user. Then it's typically stateless, walled gardens, silos of operation, then context isolation. The context of each agent is isolated from each other. So yeah, those are the characteristics of this design pattern. Now, we've definitely seen how this kind of pattern works when we're looking at workflows, in LangGraph. The routing workflow, the router workflow kind of works similarly to this. But let me just show you how the fan-out process looks like. That's the process of sending different tasks to different agents. So let us go to pseudocoder. And let's say after the classification step, we get something like this. We get this variable, classification, which is a list. Classification. Oh, yeah. So we get this variable, which is a list. And inside, we get dictionaries of each classification. And what this will typically be is that we'll have, let's say, a variable called source. Source is going to be the name of the agent that is going to take it up. Let's say we have archaeologist here. Now I'm wondering why I picked this very complex names. So archaeologist, then we have query. That's the instruction that is to go to them. So this will just be a bunch of blah, 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 blah. So let me just do that. So we have that. You can name this agent, you can name this source, whatever. Source is just trying to depict the fact that you are probably doing a research that involves you querying different sources. So this is geologist, has his own query, and we have meteorologist, and he has his own query. So this is the result of your classification step. This is what you save in state, a list of how the task has been broken down into the sources to query and what we're going to be querying. So with this information, you can then add a routing function to your graph. You can add a routing function to your graph using send. This is where send is the main player, is the star of the show. You add a routing function using send. And what send is going to do is that it's going to get that particular classification from state. It's going to get that classification from state. It's going to loop over it, and for each of them, it's going to send, or it's going to return a send object. It's going to return a send object, which the agent is going to be the source, and the query is going to be classification query. Yeah, that's going to be the state for that node. So, or that agent. So it would pick the agent or the node and then send the context here, picking it from this breakdown that I just did. And when you want to do the synthesis, you can always use a state variable that has a reducer. For example, let's say results. Let's say you have results in state, and this can basically be an annotated state channel, which is a dictionary or a list, which is a list, and you can use the add function from operator. Use the add function from operator. Oh, this is very, very important. Else, each result is going to override the previous one. Each result is going to override the previous one. So you want to make sure that you have this with the right reducer. Am I doing this right? I think it's this. Yeah. So you make sure that you add the data type. This is going to be a list, and we're going to be adding to the list. So we add all the results, and then you can then process the results yourself. You can take the result state variable, and you can loop over it to generate your final result. Here you do the classification step, you do the fan out step using send, and then you synthesize by making sure that each agent is sending their results to this results variable that you have added a reducer, an additive reducer to. So yeah, that's how you ensure that your results are collated. Now let's go back. An important thing to discuss, because it will most likely be a question that has been going across your mind as we're working on this, or rather as we're discussing this pattern, which is how is it really different from sub-agents? How is it really different from sub-agents? So let us dedicate this section of the video to router versus sub-agents. Router versus sub-agents. Let's dedicate this section to router versus sub-agents. And let's see how they compare. The first heading we're going to be discussing this under is routing decision. How they make routing decisions. Let me see if I can have some sort of tabular stuff here. So this will be router, and here we have sub-agents. Router and sub-agents. So first is routing. How do they make routing decisions? Routing decision. Let's be explicit. Routing decision. A router makes his routing decision through classification, through a classification step. That's how a router makes his routing decision. By the way, I think I need a line. I think this would, yeah, let's do this. Some lines here. Let's put another one here. Yeah, that's good. So, a router makes its routing decision through a classification step. So it's a very structured step, and it produces a structured output. However, the supervisor does dynamic reasoning. Dynamic reasoning. So the supervisor is the one that uses an LLM to determine what it should call, when it should call it, how it should call it. Should it call something in parallel, then one order later? The reasoning is dynamic. So that's why they are added as tools, because LLMs can better handle tools. So a router's routing is structured, uses a classification step, breaks it down into a bounded list of actions, whereas the routing for sub-agents is dynamic. The next is when routing happens. When does the routing happen? When does the routing happen? For the routing is always once and upfront. It only routes once. It does its classification step, determines where it should go, routes, and is done. It's not going back and forth, it's not coming back. It's going to route in parallel once, synthesize the result, and everything is done. Upfront and once. But that of sub-agent goes on continuously. And even during... No, that's not right. It goes on continuously during the conversation. Yeah. That of sub-agent goes on continuously during the conversation. So it keeps getting context back from results of previous routing decisions and determining whether it's to make another routing decision or to return the final answer and stuff like that. So everything is dynamic. Next is parallelism. Parallelism. In the router pattern, parallelism is native. Parallelism is the native execution. Like I told you, don't use router if you don't have parallel operations to run. Don't go there. So it's native, that's the native execution. For sub-agents, it's possible, but supervisor controlled. It's controlled by the supervisor. It's possible, but the supervisor gets to control when it is done. So it's a runtime decision. Also, how does multi-turn happen? How does multi-turn happen? In a router, multi-turn is stateless. So it's typically stateless. You just run a single request through, it breaks it down, runs it in parallel, and that's done. The execution step is not trying to get feedback and decide on what next to do. So other information is not necessary. Whereas in sub-agents, you need that state to operate. So this is naturally stateful. Of course, you can always add a checkpointer to your router and run it on several turns, but it's just good for running parallel tasks straight up and getting your results back. So that's how multi-turn happens. So what about subtasks or sub-questions? In a router, this is generated by the classifier. So the classifier already generates everything that is needed, any follow-up questions, any 1A, 1B, all those kind of multi-level querying. Meanwhile, in sub-agents, this is generated by the supervisor on demand. It's generated by the supervisor on demand. So the whole dynamic thing is still going on. Next, how is synthesis done? How are the results collated? Since both of them are going to be working with multiple agents, how is the entire result going to be collated? For a router, there's a dedicated synthesis step. For the router, there's a dedicated synthesis step, as we have seen. However, for sub-agents, the supervisor synthesizes. The supervisor synthesizes for sub-agents. Next, how about complexity? Complexity. And you have guessed this. In my opinion, this is more structured. Not my opinion, actually. It's the way it is. It's more structured and explicit. So we can say that it is less complex. Whereas once you start dealing with flexibility and dynamism, which is very, very good, things get more complex. So I believe sub-agents can really get complex with time, especially when it comes to debugging and tracing and all that. Now, what is this best for? What are they best for? Router is best for situations where you have known verticals. For example, like a parallel research. Parallel research. Let's go a step down. This is the last point anyway. Then sub-agent is better for dynamic routing and a conversation scenario. Like I said in the sub-agents video, I'm planning to create a course where we get to build ChatGPT from scratch with all its basic features. And I feel that sub-agents is going to be the best for that. It can hold the conversation and can call multiple agents on the ground to perform more specialized tasks. So yeah, these are your differences. These are your differences between the router design pattern and the sub-agents pattern. This is your wall of decision, your decision framework. And I hope this finally answers any question around the differences between the router pattern and the sub-agents pattern. Now let us take a look at benefits and trade-offs. Benefits and trade-offs. The benefits on this side, back to writing benefits. And and trade-offs. Get rid of this out of here. So benefits and trade-offs of the router pattern. First super obvious benefit is parallel execution. Parallel execution is native to this design pattern. So once you have a system that requires parallel execution specifically, this is a strong pattern to consider. So parallel execution, which provides significant latency reduction compared to sequential flows. Next, when you have targeted queries, when your queries are defined and targeted, you want to consider the routing pattern. If it's a system where you know that out of the whole task, each agent is going to get an optimized sub-question, just go with router. Go with the routing pattern. Next is selective routing. So a bunch of the characteristics are basically their advantages. Only relevant agents are invoked. Also, there's clean separation. Context doesn't leak into one another. Each agent gets to do their work without being bothered by others' operation. Also, it is scalable. Yeah, it is scalable. You can keep adding specialists and it knows when to call which, and it calls them in parallel, making it very, very efficient. So vertical agents just working on their specializations. Also, it's predictable. It's quite predictable. I think of all the design patterns, it is the most predictable. Very predictable. You know the steps, you know the decisions it will make, you know how it will make them, you know how it will finish off. So it's just awesome. And the more predictability, the easier things are to debug. You have explicit routing logic, straightforward when it comes to debugging. Also, cost control. Cost control is another strong benefit. You know which agents will run, you know how they will run, so you can kind of estimate what they will consume in terms of tokens. So that would help you because when each agent runs, you can even do things like configuring the model, max tokens. So based on how elaborate you want the work to be, for example, in research, which is one of the strong use cases, if you want the research to be very, very elaborate, you want to allow it to use as much tokens as possible. But if it's just going to be like compact information that you want to get from each research by each agent, you can set a max tokens. You know, don't use more than 5,000 tokens. Just use more than 5,000 tokens. And you can do that because you know that you can still get enough information to produce a reasonable final result. But if you limit tokens when you're using sub-agents, it might cut off their decision making, it might cut off their flow, and it will just truncate the entire process. So here you have more grip on the cost. Now let's look at trade-offs. First, it is stateless by default. So each independent work is independent. You will need extra work for multi-turn conversations. So I wouldn't advise them for multi-turn conversations, but if you need to, you will have to do more work with checkpointers and feeding back states to every single agent and bundling it up with the classification step and all that. So that can introduce some extra complexity. Also, there's the classification overhead. So you have to actually call an LLM at that point. Yeah, you have to call an LLM to actually help you break that down. The predictability can also become quite rigid. So it can't dynamically make decisions. The decisions don't go further than just breaking things down and picking the agents to work on it. There's no dynamism mid-execution. It can't adjust its flow. It's just, say, here's go, and it goes. So you can't make edits or have some sort of intelligent rerouting. So that's one more thing. Also, the quality of the synthesis. You have to provide a strong synthesis prompt to make sure that it is synthesizing correctly. If you provide weak instructions, it's just going to give you a very subpar report or result. So you have to make sure that you explicitly detail how you want the response to be presented. Another thing is that there is no agent interaction. Yeah. It is one of the few systems that the agents don't collaborate in any form of way. Even sub-agents, they, in a way, collaborate through the main agent. They can feed off each other's context. But here, nothing like that. The agents don't interact at all. Agents can't consult each other. You have to be refeeding context if need be. And that is not even the best use case for it. So you might want to pick a different pattern at that point. Also, query decomposition. This is similar to synthesis quality. If you don't provide good instructions on how the classifier should split the query, you are going to be splitting wrong, delegating wrong, and at the end of the day, it's going to be garbage in, garbage out. So your eventual response or results is not going to be good enough. And it can even be almost useless. So you want to make sure that you write proper prompts for your classifier so that the model can properly classify your task. So those are our benefits and trade-offs. And if you have been following, you know it is time. If you have been following from other videos, you know it is time for use cases. It's time for use cases. So we reduce these guys and talk use cases. What are the use cases for the routing pattern? The first one is, may have guessed it, multi-source knowledge. Multi-source knowledge operations. So you need to pull knowledge across different sources, search across different sources in parallel. The sources can be documents, they can be websites, they can be discussion boards, they can be from code. Yes, this pattern can help you excellently. Another use case is research queries, which is the example that we have been riding on throughout this video. Research queries. So you consult multiple databases, multiple information banks for research purposes. Also, if you want to compare, if you have comparison questions, who is better, Ronaldo or Messi? So you spin different agents, one with good knowledge of Ronaldo, one with good knowledge of Messi. They start collating stats, they start going through their football history, fitness, decision making, even soft skills like how they interact with their players, their coach and everything, and then bring together a full comparison between Ronaldo and Messi. So if you have comparison questions, you need to compare two things. It's very perfect. It's very perfect for that use case. Also, aggregation. Aggregation queries. If you just want to pull, let's say, you want to do a research and say, what are the top 5 agentic tools? What are the top 5 agentic tools? So you can go out, do that research, and then synthesize and give you the top 5 agentic tools. You can also use it for opinion gathering. What do news websites say about the COVID vaccine? To go out, pull information from different news websites, and give you different opinions from different sources and how they compare. Also, it is very good for operating RAG pipelines. So if you have RAG with multiple retrievers, if you have a RAG system with multiple retrievers, you can perform agentic RAG, multiple retrievers, can perform agentic RAG and have this pull from a database, pull from different vector stores for different types of content. You can just pull from different sources and collate them into a single context. So that's another thing that you can use this for. Also, API aggregation. API aggregation, you can use it to call multiple APIs in parallel and synthesize their results. Most of these things will be done through APIs anyway. So this is more like a foundational use case that kind of covers a lot of these other guys, especially the first 4. Yeah, all these things will be done through APIs. So any type of API aggregation you want to do, this design pattern, which is a routing pattern, can help you with that. And that's the routing pattern.